Ok, così. Quindi qua dovrebbero vederci, no? Sì. Direi di sì. Disattiva il video. Lanciare la luce accesa. Oh, pazienza, senti. From Zoom, can you hear me? Okay, thank you. And do you see the screen? Okay, perfect. Thanks. Okay, welcome everybody. Would you mind if I put the mask off? Okay, thank you.
Thank you.
Welcome to this tutorial. We are, this is a full day tutorial done by me and Federica. And the title is Inside Plato's Door because
Stiamo qui.
Aspetta, che va. Okay.
Ah, fantastico.
Because according to the tradition, there is a engraving on top of the Academia of Plato that says that no one ignorant of geometry could access the Academy. And the idea today is to open this door by reviewing some geometric stuff that we are addressing in the first half of the day this morning. And then in the second part, we are going to see some more advanced application. So the idea is that if you are already super familiar with the multi-view geometry and let's say camera calibration, fundamental matrix, and that kind of stuff, I suggest you to spend your time in a different way this morning. Maybe you can attend other tutorials because this morning we are going the topic are for part one, for non-expert. And of course, you are welcome, you can stay here. But the interesting things are going to happen in the afternoon with Federica. And so, how many of you are familiar with stereo vision and dazzling geometry? Just to have, okay. Okay, maybe consider to come later. Who is not familiar and is the first time or almost the first time who's going to see this thing? Okay, so this tutorial is for you. So you are welcome to interrupt, ask questions whenever you want, because we are going to set up the notation, which is quite standard. And I don't know if you, Federica, want to give a teaser for what's going this afternoon.
Okay, we'll probably introduce the basics about multi-view geometry, and then in the afternoon we will see what is the process for producing reconstruction from images, such as in this example, and so we will address the problem of structure connection. And in particular, I will show you taxonomy of existing approaches, including what the famous one, like sequential structure from motion, and also other ways of approaching the problem. And I will also explain some theoretical assumptions that are required for some specific approaches.
Okay. So here you can see an example of the output of structure from motion pipeline. So you basically have some images and reconstruct both the pose of the cameras that acquire the images and the position of the points. We are going to just stop at this level of the model we are going to obtain, so to sparse on cloud, of course, there is other work that can be done. And in order to give you an overview of what we are going to address this morning, so you can decide what is best for you, I'm going to show you what are the topics we are going to address this morning. We are going to do the rec at 10. And for the first part, we are just going to use some basic projective geometry. So a mathematical formulation that allow us to represent in a very nice way the geometric entities we are going to do. And then we are going to see the anatomy of the camera, so some single geometry, how the camera can be modeled, and the problem of interior orientation. So how to position the camera with respect to a word reference frame. And then we see the best tool for stereo vision. So basically the fundamental metrics and the essential metrics are geometric entities that encode the pairwise relation between two cameras. And we are going to conclude before the lunch break with some rudiments of robust estimation, particularly at duality class. And the main aims of this morning is to we are trying to, so this is this topic there are books that address this topic in a very principled way. So we have only a morning, so we are going to have an overview of many of this topic, and the idea is just to grasp some intuition and to be familiar with some standard techniques. Okay, so I will stay here, no problem. Okay. So this is the program for this morning. Of course, you are very welcome to interrupt me when something is not clear, and ask a question as you wish. So
I don't see the slides.
Okay.
Can
you hear me now?
We can see you now and hear you, but we don't hear it. I see the slides.
Okay, and you cannot see me.
We can see you now, but we don't see the slides.
But not the slide?
Yes.
Okay. Now?
Perfect. Thanks.
Okay, you're welcome. Okay, so far so good. I will not be offended if sometime you decide to leave the room and come this afternoon. Okay, perfect. So let's start. So the starting point is the geometric model of pinhole camera, which is of course an abstraction. And the main ingredient of our single view geometry are this one. So we have an object, a 3D object, we are going to represent, and we are going to represent by means of the points that lie on the 3D object as capital letters. Then we have a center of projection here, which is just a point in 3D space, and we have an image plane, phi, which is this green guy here. And the whole theory we are going to develop is based on an intersection between the optical ray that is the line that passes through the center of projection and intersect the object point. This line has an intersection with the image plane, and this point, which is the intersection of the ray with the plane, is an image point. And we can model by means of simple Euclidean geometry
the coordinates of the image point, because you see that here we have basically two triangles. One defined by C and lowercase m and p. So basically you define a reference system, a 3D reference system, which is centered in the center of projection. Okay, then you have you fix your reference system in a way that the z-axis points towards the image plane. Okay, then the image plane is at a certain distance f from the center of projection, and you can draw this triangle. So you imagine to see your camera from the side. Okay, so here we are seeing only these two axes. Okay, and you have this triangle here and this triangle here. Okay, and you see that this distance from C to the z coordinate of capital M is proportional to the distance from the image plane, as the distance, so here the y coordinates of capital M is proportional to the y coordinate of lowercase m. So by putting down into an equation, you get that you can relate the coordinates of the word point with respect to the coordinate of the image point. It's just a matter of similar triangles, okay? And you can see that, so a point M is mapped to a point small m in this way, and you can see that you have a division by Z. And actually, this tells us that the camera projection equation that relates a 3D points with an image point is not linear, because you have a division by Z. And this actually is responsible for the perspective effect. So the reason why the length of the segments are decreasing in this way. Okay, and basically for this hour we are going to develop some theory to make this projection linear. Okay, and you can see that also something happens that is quite different from the Euclidean geometry, the standard geometry we are used to, because here we have in the world we have let's say two 3D lines that are parallel, so they do not have a point of intersection. But when you imagine, you get a picture of these two lines actually have an intersection that does not exist in the real world. And if you imagine to collect all the possible intersection of parallel line, you get a imaginary line, which is the horizon, the line here depicted in green. Okay, so the idea is how can we model these points that do not exist in the real world. And to do so, we can make a picture of the situation we have seen so far. So imagine to have two planes. One plane is the blue one, the horizontal one, and imagine to have a camera. So a camera for now is just a point C and a image plane, the plane, the green plane. Okay, and you can see that by taking photos, taking a photos actually means just to take a point on the blue plane, okay, collect it with the camera center, get the optical ray, and intersect it with the green plane. Okay, so capital A becomes lowercase a in this way. And you can see that by doing so, this perspective equation defines almost a bijection between the two planes, because there are some points that are not mapped between the two planes. So you can see what happened for the points that lie on this line. You can see that there is no a point in the blue plane that actually is mapped to this point here, okay? Because the optical ray would be parallel to the plane, so you have no intersection, and you cannot back project the point there. And the same apply here for this line L, okay? Because the situation is quite similar. The optical ray do not intersect the green plane, okay? And so what we want to do is to extend this mapping to the two plane by augmenting the plane with some additional point in order to make this projective mapping a bijection and to preserve continuity, okay? And the idea is that we can add to the blue plane a line, the line depicted there that is not a standard line because it does not exist in the Euclidean plane, that collects some ideal points that are mapped to the horizon, okay? And we call this point that lie on this line here ideal points, and they will be mapped to a vanishing point. So the image we call a vanishing point, and you can recognize this situation here, okay? You have here you have the two lines, okay? Parallel lines, we will see that parallel lines have an intersection on those lines that they are missing in the real world, but they will have on the ideal point. And so you have you can back project this point to a vanishing point in the image plane. So far so good? Okay, perfect. So here is just a picture we are going to use a lot in this slide, that by the way will be available I think after the tutorial. And so on the left I depicted the Euclidean plane, which is of course we have to draw it in some way. It's unbounded, but here we draw as a square. And on the right we have the projective plane, which is the Euclidean plane, the blue square, plus the line collecting the ideal point, okay? And the idea is that here you have a bunch of parallel lines, different families with different colors of parallel lines, and for each of these family you get a vanishing point that is the point of intersection between this family of parallel lines. Okay, does it make sense? And this is just an intuition because this thing can be made rigorous. And basically, you build the projective plane by using homogeneous coordinates. So the projective plane is just the triplets of real points minus the origin, minus the 0, 0, 0 coordinates, plus an equivalence relation defined in this way. Two triplets of points are x, y, u, x prime, y prime, u prime are equivalent if exists a scalar different from 0, such that the x equals lambda in x prime and so on. Okay, so there is a multiplicative factor of difference between the triplets. Okay, and the projective space is just the quotient space of this equivalent relation. So if you write the point, I don't know, let's see if this work. Sorry. It's not working. Okay, no problem. Okay, no, it's not working. Okay, so basically, in order to express this condition, we are, instead of using a comma, we are using a semicolon, because what matter are the ratio of the coordinates. So the point 1, 1, 1 is the same of the point 2, 2, 2, okay? Because in this case, there is 2 that lambda equals 2, and you get that they belongs to the same equivalence classes, okay? So in a more easy way, we can think that we have the standard Cartesian coordinates in the Euclidean plane. So we have pair of coordinates to represent a point. In order to work in a projective space, you have to add an additional coordinates, okay? And these, you can think that these coordinates work as a flag that allow you to distinguish between standard points in the Euclidean plane and ideal point. So you have that you can augment the coordinate of this point with a 1, and in this way you can you can represent points on the line at infinity in this way, as a point with the last coordinate equals to 0. Okay, and so in this way you have a quick test that allow you to determine if a point is a standard point, the last coordinate equals 1, or if whether it is an ideal point, the last coordinate equals 0. Okay, and of course we can do also the reverse operation. So we can start from the projective plane and see what is the Euclidean plane that lie in that projective plane. And the operation consists in just dividing the coordinates for the last, the projective coordinates for the last coordinate, okay? In this way, you can you get rid of the last element of the triplets. Of course, you can do it for all the points, except you have to divide for the last coordinate. You must ensure that the last coordinate is different from 0. Okay. So you can obtain this red arrow for all the points, but the ones that lie on the line at infinity. Okay, which in fact is a line, even if we draw it by a circle in order to represent it in some nice way, and then I'm going to provide you a nicer model of the projective plane. But you can see that that line satisfies a linear equation because is u equals 0. Okay, so is just a line as x equals 0, y equals 0, and so on. Okay, and of course this construction can be extended also to spaces and spaces with higher dimension. The trick is just to, if you want a 3D space, you have to consider a 4-dimensional space and put on that space that relation, this one. Okay, so just define homogeneous coordinates, so augment by 1 the dimension and just look at the ratio of the coordinates. The points satisfying the constraint, the last coordinate equals 0, are geometric entities of ideal points. In the plane, u equals 0, define a line, the line at infinity. If you are working in the space, a single linear equation define a plane. So in the projective space, instead of having a ideal line, you have an ideal plane, the plane at infinity, which collects all the direction of family of parallel lines. Okay, in 3D, you have a notion of parallel lines, all the parallel lines met in a point on the plane at infinity. Okay, does it make sense so far? Perfect. And so you can see that points in P3, so in the projective space, are just represented as 4 points, and what matters is the ratio between those points. Of course, we are going to use the convention that the last coordinate is the one that denotes if a point lies on the plane at infinity or not. Okay, and what we have gained so far by this construction? We have resolved some strange things that happen in the Euclidean plane, because if you think of that, in the Euclidean plane you have some asymmetries, because it's not true that for every pair of line have an intersection, okay, because there are parallel lines which must be treated differently. Here, instead, we have that for every pair of points, there is a line passing through them, and the converse is also true, because we have that for every pair of lines, that there is a point lying on them. Okay, so this kind of symmetry between the role played by points and line is called duality, and it provides also algebraic formulation. So you can express this factor by simple algebraic rules. For example, you can try yourself and see that the cross product between the projective coordinates of 2 points give you the 3 coordinates of the line, or the line passing to them. And you have that you can, just by replacing points with lines, you get the intersection. So if you perform the cross product between 2 vectors representing the coefficient of a line, so I forgot to tell you that we have the equation of a line in this way, okay, and we can just store the coefficient of the line in a homogeneous coordinate, because what actually matters here is just the ratio between the coefficient. If you multiply the equation of a line by some constant, which is different from 0, you get the same line, okay? So the coefficient of a line are the good candidate to be expressed by homogeneous coordinates, because actually it's exactly what's happening here, okay? It's all important the ratio between the coefficient of the lines, not their actual value. So you can represent the line as homogeneous coordinates, and this is the reason why you have this kind of duality, okay? And if you get the equation of a line and you arrange them in an homogeneous vector of coordinates, you can just perform the cross product between the coefficient, and you get the intersection, okay, this point. And another nice thing that can be seen algebraically in a very easy way is just to perform the inner product between the homogeneous coordinate of a point and the homogeneous coordinate of a line to see whether they met or not, okay? If this equals 0, you know that this point line lies on that line, okay? And there is a very deep relation between point and line, and actually you can build a projective plane that represents line, okay? So you have a dual situation. So you have a standard point plane on the left, and then you can build a dual plane where you depict the relationship between the lines and points in the standard plane. So basically, here I have this red line. I can represent this red line as a point, okay, in the dual plane, because I just take the coordinate and build an homogeneous vector of coordinate, okay? Then I can do the same for this blue line here. far so good. So this blue line give me a blue point in the dual plane. Okay. Now, of course, I can take linear combination of lines in the standard point plane, and what I get is a pencil of lines. Okay. If I just write lambda, the first line, the red line, plus mu, the blue line, I get a line that belongs to the pencil defined by these two lines. Okay, of course, it passes to x0 because both the red and the blue line pass through x0. Okay, the support of the pencil. And by varying these two coefficients, I get all this green line. What does it mean? What does it mean? That it means that in the dual projective plane, I just taking linear combination of this point here, the red point here, and the blue point there. Okay, so the pencil of points here describe this line. Okay, is it clear? Almost. Does it make sense? Okay, so you can identify. Okay, so you can identify this line here, this red line here, with all this line, which it's not convenient. We can represent this line here by the support of the pencil. Okay, so here you can see that you have a bijection between points that are represented as, between lines in the plane on the left, which are represented as point in the dual plane, and lines in the dual plane, which are represented as pencil of lines, which boils down to the support, to the point. So you see that you have a line, then you get a point in the dual plane, and if you get a line in the dual plane, you get a point in the standard plane. And this is the reason why these holds. Okay. Okay, and in general, you have a machinery to build theorems that are true in projective geometry, because for this reason, whenever you have a theorem that expresses some properties about line and point, you can interchange their role and get a true statement. So the principle of duality tells that a true statement involving points, lines, and incidence between them results in a true statement if the words point and lines are interchanged. So we have already seen an example of this fact, because we know that 2 points are incident to a unique line, and by duality we have just to replace the terms, and we get the 2 lines are incident at a unique point. Okay, this is an example. And so far everything is clear. What we have done so far was just, okay, let's start from the camera projection. Okay, we take the picture of 2 parallel lines in the 2D, and we see that they have a point of intersection that does not exist in the real world. Okay, so we analyze that situation as a mapping between two planes, and we see that the relation between these 2 planes was not a bijection. Okay, so we say, okay, let's add some points that does not exist in the actual plane, the ideal point, and we see that this boils down to defining homogeneous coordinates. And I'm not sure it's easy to see that construction, but we are going to see a geometric model of this situation later on. And then once we get to the projective plane, we just analyze points and lines, and we see that there is a strong relationship between them. We have a symmetry that does not exist in the Euclidean plane. So the role of lines and points can be interchanged. And now we are going to add some other, let's say, element that can live in the projective plane. Okay, one of them, so we have points, we have lines, the second, the third thing that we can add is quadrics. Okay, so basically we just write down some polynomial equation in the second degree, and we get the well-known conics, which are we already familiar with, and in projective space can be expressed by means of symmetric metrics, because a conic is defined as the zero set of a quadric homogeneous polynomial. And by using homogeneous coordinates, you can see that if you arrange the coefficient of the conics in this way, okay, you get your second degree homogeneous polynomial. Okay, so you can identify a conic with a 3 times 3 symmetric matrix. Okay, and according to the determinant of this conic, you can have proper conics. This one, ellipse, parabola, hyperbola, and also degenerate conic when the determinant of the conic is not full. Okay, and here again you have a nice way to write down the conic, because if this line is L and this line is M, you can identify this line with their homogeneous coordinates, and you get that the conic defining this geometric set is just the product of the sum of the product of this vector. So this is a 3 times 1 vector L. You multiply by the transpose, so you get a 3 times 3 matrix, and then you add the M multiplied by the transpose of L, and so you get a matrix having rank 2. Okay, and of course, wherever L and M are the same, these specialize to this equation. But since we are working in the projective plane, the multiplicative factor 2 doesn't matter, and so we can just write the equation of the conic in this way. Okay, and of course, we have this nice property that we consider tangent to a conic. And we have a nice way to get the coefficient of a point of the line which is tangent to a conic. Just take the 3 times 3 matrix of the conic and multiply it by the coordinate of the point. Okay, so you are multiplying a 3 times 3 matrix by a vector. You get a vector, and this vector store the coefficient of the line which is tangent to the conic Q at the point X. Okay, and you can here is a proof of this fact that I'm going to skip, but you can find it in the slide. And the important and the nice thing is that if you consider all the lines tangent to a conic, they satisfy a quadratic relation. Okay, you can verify this. And what does it mean? It means that a line in the point plane can be identified with a point in the dual plane. Okay, so if we know that line tangent to a conic satisfy a quadratic relation, it means that the line in the dual plane, which can be identified a point, also satisfy a quadratic relation. Okay, so we can, by having a conic, we can consider all the line tangents to the conic. Okay, lines can be as point in the dual projective plane, and we know that those points satisfy a quadratic relation. So basically, we can associate to a conic a dual conic. Okay, which is just the collection of lines tangent to the original conic. Okay, and of course we can have also, as we have degenerate conic, we can have also degenerated dual conic, which are conic that has not full ranks. And in particular, we have that if a dual conic has rank 2, then it consists of all the line passing through 2 points. Okay, and here you have the picture. Okay, so in the dual plane, you have a degenerate conic, which consists of 2 lines and the point passing through them. But you know, by the principle of duality, how to represent this in the original projective plane. You have the green line, which can be identified with a green point on the left. You have the blue line, which is just a blue point in this space, okay? And actually, it's not only a point, it's all the lines passing through that point, okay? And this point here in red is just the line connecting the two, okay? So here you have a picture of the degenerate dual conics, okay? And by the principle of duality, you can see for every conics which can be its dual counterpart, okay? And we are going to use a little bit both conic and dual conic in a few moments. Okay, so far so good. Everything is clear. Stop me otherwise. Okay. So by adding the ideal points to the plane, we get a bijection between these 2 points, and so we can, by making use of homogeneous coordinates, we can represent this bijection, which we have defined geometrically, also algebraically. Okay, and the nice things about homogeneous coordinate is that we can express this expression, this mapping as a linear transformation. So we have triplets of points, triplets which define homogeneous coordinates in the green plane, triplets which define homogeneous coordinate in the blue plane. Okay. And we can just represent that transformation using a 3×3 invertible matrix we are going to call homography. Okay, so what is an homography? The homography is just an invertible mapping between projective plane, okay, spaces in general, depending on the dimension of the matrix. So you have you have 2 projective planes, two projective space. All the invertible transformation can be expressed as invertible matrices. Okay, so just look at the determinant of the matrix. If it's different from 0, this define an homography. And of course, since the homography operates on homogeneous coordinates, also homography are defined up to a multiplicative factor. Okay, and here in this slide, we can see how homography operates on all the entities we have defined so far. For points, it's quite straightforward. You take the homogeneous coordinate of a point and you left multiply it by the matrix. And for lines and conics and dual conics, things are a little bit different. But the important things to remember is that it's possible to just take the coordinates of a line and multiply it by the transpose and inverse of the homography, and you get the mapping of the maps, the image of that line. Okay, and because an homography is a linear transformation, it of course maps a line to a line, and a similar transformation holds also for conics and dual conics. And the important things is that the invertible matrix define a group of transformation. So a group is a mathematical structure where you get the identity element, which does not do anything. And then for every element, you get the inverse. And when you compose 2 elements of a group, you get an element that lie inside the group. And invertible matrices are a group. And the important things that we want to address here is that by a very general perspective that is due to Felix Klein, geometry is the study of properties that are invariant with respect to a certain group of transformation. For example, here you have a bunch of triangles. You can ask which are the same triangles. Okay, and to answer to this question, maybe you answer the blue and the red ones. These two triangles are the same because they have the same angles. Okay, but what you are actually doing is that you are performing a similar transformation between these two triangles, and you decide that to be the same two objects, there must exist a transformation in a certain group that maps the first object to the second one. But depending on the type of the group you are considering, you are defining different idea of same triangle or same object, because different properties are preserved or not. And the idea is depicted here. So we start from the more general group, which is the group of homographies, which preserve the more deep properties of geometric objects. For example, incidence, collineation, and tangencies, and so on. Parallelism not. Sorry for the mistake. And then you have affinities, which are metrics having this form, which preserve more specific properties. For example, the ratio between parallel lines, parallelism, the ratio of areas. And if you consider more specific group, for example, similarities, which are metrics that can be written in terms of rotation, scaling, and translation, you get more specific properties that are preserved. For example, the angles, the ratio of the angles, the ratio of the areas. And when you get to the Euclidean group, you have that very specific properties are preserved. For example, the length and the angle and the area. So if we play the Felix Klein game here, we can say that these two squares are the same if we stay at the Euclidean level. And also these two squares are the same if we consider similarity transformation, because there exists a similarity that maps the red square to the pink one, and so on. So we get that in general, as long as we are able to consider the more general class of transformation, homographies, we can map the red square to the yellow one here. Okay? And the idea that we want to address here is that it is possible to recover some Euclidean properties, so some properties that lies at the most specialized group, even in the projective space. And we are going to see one projective Euclidean invariant that is hidden in the projective plane, which are the circular points, and one Euclidean invariant which is hidden in the projective space, okay, which is the image of the absolute conic. I just want to give you an idea of how this thing works. So more formally, in a projective space, we can consider some specific subspace, which are the subspace having a coordinate, one coordinate different from 0. Okay. So what happened in our drawing? We have the projective plane, and we consider these affine, and we call these pieces these subset affine pieces. And we have, since we have in the projective plane, we have 3 coordinates. We have 3 affine pieces, one for each coordinates. And you can see that the first one, so the one having the third coordinate different from 0, so u different from 0, is the one that corresponds to the standard Euclidean plane. Okay, we already seen that. And the other one are just the projective plane minus a given line. Okay, minus this line here and this line here. Okay, and the important things is that the subgroup of projective transformation that preserve the line at infinities consists in affinities. So let's see in another way. Of course, projectivity maps line to line. Okay, so if you have a projectivities in a projective plane, you can map also these purple lines to any line in the plane. Okay, and this happens for all general projectivities. Affinities, the ones that encode affine properties, for example, parallelism and so on. Okay, are projectivities. Okay, because they are a subgroup of homographies, are those projectivities that fix the line at infinity. Okay, that do not move the line at infinity. Okay, so the line at infinity is a fixed line. Of course, a point on the line can move. Okay, but the line remains fixed. So it's a fixed line, not a line of fixed point in general. Okay. And so there exists this theorem that say that the subgroup of projective transformation that preserve the line at infinity consists in all the affinities of that form. Okay, having an invertible 2 × 2 matrix in the top left corner, then a translation, and then 0 and 1. Okay, so we have a geometric entity, the line at infinity, that if remains fixed, fully characterize a subgroup of transformation. Okay, so in another word, when a plane at infinity has been chosen, affine properties can be established. For example, 2 lines are said to be parallel if they intersect at a point at the plane at infinity. Okay, now I'm going to provide you a different geometric model for the projective plane. Basically, you start from triplet of points, okay, and we say that triplet of points identify the same points if there exists a non-negative multiplicative factor. Okay, so basically we are considering all points that lie on that line. So if you take this point here, which is x, y, and z, the same, this point here, which is, let's say, 3 times the first coordinate, is the same. Okay, so you have that points belonging to the same ray represent the same projective point. Okay, so let's consider all the ray stemming from the origin. Okay, all the points identify an equivalence classes in the projective plane. So we can, let's say, see for a canonical representation of that classes. And I say that I take the unit sphere, and I take as the representative of that classes the intersection between the ray and the unit sphere. Okay, so I have identified every class of equivalence with a point on the unit sphere. Okay, and this is not very convenient because I want a model for a 2D object, and here I am in the 3D. Okay, no problem. I can project the point on the plane z equals 0. Okay. Okay, but what's happened? That for the points that lie on the hemisphere, okay, on this circle, we have that there is an antipodal identification, okay? Because these points and these points are the same, okay? Because they belong to the same ray coming to from the origin, okay? So what's happened is that when you have a conic, take an ellipse in the plane and imagine to move the ellipse towards this purple line. What's happened is that you push your ellipses to the line since it has a single point of intersection. So the conic is tangent to the line at infinity. But if you push further the ellipse, what's happened is what's depicted here. Okay, you have that the line at infinity becomes secant to the ellipses, and you have that this guy here is identified with this guy here. Okay, so basically, if I work here, I exit here. Okay, I come up here, and this is the reason why from a projective point, all the irreducible conic are the same, because it's just a matter of how they intersect the line at infinity. But when you get the affine pieces, you get different affine traces. You get three different types of conics, okay? Because if the conics is not tangent to the line at infinity, you get the ellipse, okay? Sorry for the mistake, I will fix it. Then when you have a single point of intersection with the line at infinity and you remove the line at infinity, you get the ellipse, okay? So, sorry, the parabola. They are messed up. And when you get a secant, you get the hyperbola, okay? Because this guy here end up there, passing through the line at infinity, just to give you an intuition, okay? Tell me if something is not clear. Okay, so to sum up, the relation between affinities and homographies. We have homographies. We are studying the properties which are invariant with respect to certain group of transformation. In the projective plane, by looking at homography, we have a very high level properties, such as incidence and so on. We want to recover more structural properties, some affine properties, for example, parallelism and so on. But by identifying a geometric entities, okay, we can characterize a subgroup of transformation. So affinities are those homographies that keep fixed the line at infinities, but points may move along the line at infinity. Okay, so this is an homography, the first one, this one here, because the line at infinity stay fixed, okay? And this one instead is an homography, a general homography. And you can see because the line at infinity is mapped to another line here in the plane, okay? For example. But if you are able to find a transformation that maps the image of the line at infinity in its canonical position, okay, that we know is this one, 0, 0, 1, we are able to recover the affine properties of the transformation. And I'm giving you an example. Here I have an image of a floor, okay? It's taken from a camera, so we can assume that the relation between the actual floor and its image is a projective transformation, okay? Which in general maps the line at infinity to some line, to some other line in the image plane, okay? So we have lose some properties, okay? For example, the length of the side of the square as different, whereas in reality they are all the same, okay? What what can we do is to recover some affine properties here. And this is done in this way. I just recover the image of the line at infinity, okay, in this image, and I send back this line here to its canonical position. By doing so, I get an affine promotion of this image. Okay, and I'm going very fast so you don't lose the coffee break. I just want to say that there exists also another geometric entities inside the projective plane, which encode not only affine information, but also Euclidean information, okay? And these entities is represented by the circular points. Circular points are this guy here, which are points with complex coordinates that has these nice properties. If you take the equation of this, how many points do you need to define a conic in the plane? 5 points. How many points do you need to define a circle in the plane? 3 points. But circle are are conics, okay? Where does the missing 2 points go? They are the circular points. So every circle passes through the circular points. This is the reason why you only need 3, because they automatically pass by these 2 points. If you take these points and look at the equation, you see that x squared plus y squared equals, they are always satisfied. And there is a theorem that is similar to the one we have seen before, which say that the circular points, which, by the way, lie on the line at infinity, okay, are preserved by similarity transformation. Okay, so again, here you have a geometric entities, which, if it is preserved by some transformation, fully characterize a subgroup of that transformation. Okay, so you have a characterization of similarity transformation. And there is an algebraic device that encode this information nicely, that instead of considering 2 separate points, we can consider the pencil of points, the pencil of line passing through that points. Okay, we have seen before that this is a dual degenerate conic, and this is called the conic dual to circular points. And the conic dual to circular points encode, therefore, some information that is strictly related to similarity transformation. And so the things to remember is that Euclidean geometry is just projective geometry plus the location of the circular points. And this is similar to what we have seen before, where the affine geometry was equal to the projective geometry plus the position of the line at infinity. Okay, and it's not a surprise, because if you see the conic, the actual coefficient of this conic, it can be used to measure angle between lines. Okay, if you take the equation of 2 lines, this one and this one, the blue and the green, you can use the metrics associated to the conic dual to the circular points to compute the angle between these 2. And the angle is an object, is a property strictly related with the similar transformation. Okay, so we can use the conic dual to circular point to measure angle between lines in image. So imagine to have the floor before. You know that the angle in the square are, or the lines defined in the square are orthogonal. when you get the image, this is not true, okay? But by having that information, that in the original plane, the square are orthogonal, okay, you can recover the image of the conic dual to circular points and bring it back to its canonical position. And this is the idea. Okay, so basically there are some entities hidden in the projective plane, okay, that characterize different subgroup of transformation. And in the projective plane, these information are lost, but with some additional information about the scene. For example, we know that two lines are parallel, or we know that two lines are orthogonal. We can recover the affine or the similarity information hidden in the images. And this can be also done in 3D, but maybe we can look at this after the break. Okay, see you in 20 minutes. And if you have any question, please come. I will be happy to answer.
I have a quick question. So, like the way we construct hyperbolas and parabolas is like you have a cone, and then you consider like the naps of a cone, and then you consider a plane which cuts that. So, depending on how the plane cuts it, like that gives you an idea of like which a parabola, hyperbola, and
yes,
or
yes,
ellipse.
Yes.
So, how does that relate, like that naps of a cone and plane cutting, relate to the stuff you showed, which is like a line at infinity? Like, where is the line at infinity when you...
yeah, okay, you're asking, I think this is a quite different perspective, because from a projective perspective, what's the matter here? The matter is that a conic is just the zero set of homogeneous second degree polynomial.
Right.
Okay.
Yeah.
Okay. And there always, if the conic is non-degenerate, there always exists an homography which bring any kind of non-degenerate conics in the same. So by a projective point of view, all the conics are the same. So there is no difference between them.
Yeah.
Okay.
I think my question, I have to reframe. So the question is like, there should be some connections between L infinity and the general way you construct the conics, right? So right now, like what we are saying is like, if there's a conic and there's an L infinity with a tangent line getting there. So if it intersects at like on the semicircle at only one point, then there is that's a parabola. Right?
Yes, but they are quite different definition, because here we are in the plane and you are building the conic as a section of cones. So you are in 3D. I'm not sure how you can see the line at infinity on that plane. Oh. So the line at infinity should be lying on the plane of intersection. So all the plane you are using to cut your cone.
But there should, like, I'm just trying to relate those two things. So one is in 3D, and this one is like you take a hemisphere and then project it on the circle and then see where the stuff is. So I'm trying to see whether the L infinity, like the line at infinity in the circular space where you use it, can that be transferred into the 3D? Like, can you see it in 3D?
I see, but I cannot figure out immediately.
Oh, okay. Yeah. Thank you.
Just wanted to discuss about versus like
the limits.
Yeah, versus like this projection.
The limits, I don't see. It's just a formulation. I don't see any kind of limits on that. It's quite my model, nothing wrong. Using it is that I'm completely disregarding nonlinear effects. So when we get the camera, I don't know if I answer your question. So we are just considering the picture, the act of taking the picture as a linear thing. So we are disregarding completely radial distortion and things like that. But of course, you cannot just here. We are just trying to do as much as possible in a short time. So yes, yes, I think so. I push the code button and I can try it.
Is it going to share that?
I think we are going to publish on the website. Okay. Thank you. Thank you. Hello. Okay. Show me.
Yeah, I think I'm not 100% sure.
Thank you.
So instead of sharing your full screen, I mean your screen,
Okay.
you share just the window of the presentation.
Okay.
I think it would be better here.
Let's
so
try.
We won't have the subtitles and.
Okay. Let me see. What I have to do.
So when maybe stop the sharing the screen and restart sharing.
Thank you. Okay, now
Restart it, yeah, and select maybe the window of the slides.
Condividi schermo.
Yeah, so maybe
This one?
Yeah.
Let's see. Thank you. Thank you.
No, but it's not here. Okay, because you have the. No, yeah, it doesn't change anything. Sorry for that. maybe.
Sorry, I'm sorry now.
No, okay. Excuse me.
Thank you.
Welcome.
Okay, can we start? How is going? So, sorry. Sì. How is going? Fine. Too slow, too fast. I understand that we have seen a lot of material in a very short period of time, but maybe the take-home message is that we are going to use projective space, homogeneous coordinates to do the stuff we need. It's a little bit abstract, the thing so far. Now we are going to delve more into cameras and photogrammetric computer vision. So we are going to be more concrete. And to conclude, just a very short insight on what is going in the projective space. So in projective plane, everything we have done so far boils down to this. In projective plane, we have a spatial line, which is the line at infinity, with two spatial points that with a dual conic, which encode some metric information. If we are able to recover, to identify this line and these geometric entities in our images, we are able to recover some properties that are not strictly speaking projective. Okay, so we can speak about orthogonality of lines and parallelism in the plane. In the space, it's the same, but instead of having a line, okay, we have a plane, the plane at infinity. And instead of having that dual, the conic dual to circular point, we have this guy here in red, which is very similar, okay, which is an absolute conic, is a geometric entities. And we know that similarity transformation in the space are exactly those projectivities that keep fixed that object. So if we are able to identify in our projective space that conic and one of his friends, that is the dual absolute conic, we are able to recover some properties that are metric. Why I'm speaking about this now? Because with Federica this afternoon, you are going to produce a reconstruction of your scene, which is defined up to an homography. Okay, so you are going to reconstruct the scene, but only up to homography. But what you can do is that, as we did for the floor, identify these geometric objects and bring them in their canonical position, which is, by the way, is defined by that equation there, by that conic. And in this way, you are able to recover also metric information up to a similarity. So you are going to promote your 3D reconstruction from up to homography, up to a similarity, which is quite powerful, quite interesting. So all these things we have done a little bit in hurry was to give you this idea. Just remind that it's possible in projective space to recover some properties that are not strictly speaking projective if you have some knowledge about the scene and you can identify these geometric object. Okay, perfect. So to sum up what we have done, we have defined homogeneous coordinate, which are coordinate defined up to a multiplicative factor. And in practice, the last coordinate can be used to determine if a point is a point that comes from a standard Euclidean space or is an ideal point. And we have seen some Euclidean invariants that are hidden in the projective space. Okay, that's all. Back to camera. Now we are going to be more concrete. Here we have the perspective equation, and we started this journey by saying that perspective equations are not linear, and we are going and we introduce the homogeneous coordinate in order to have a more convenient way to define this mapping. And this is the mapping we were looking for. And you can see that you can rewrite this equation as homogeneous coordinate in this way. Okay, and this is not exactly what maybe you can wonder what's happening here. I was expecting 2 coordinates, and here I'm getting 3 coordinates, but it's not a problem because we are working in projective plane. Okay, so the image point is a point in the projective plane. So it's not a surprise that here we have 3 coordinates, and you can always divide by the last coordinate, so by this guy here, and by dividing for this guy here, you obtain exactly this equation with the last coordinate equal to 1. Does it make sense? It is what we were looking for. Okay, what we again, okay, instead of having this non-linearity, I can express my perspective equation by means of a matrix, the multiplication for a 3 times 4 matrix, which is the camera projection matrix. Okay, and so let's denote this guy here in this way, p hat, and you see that p hat encode has information about the focal distance. Okay, for now. But which are the degree of freedom of this system? We have basically defined a reference system in the camera reference frame, in the camera center. Okay, if and we are so object in 3D, capital M, are expressed in this reference system. Okay, the blue one here. Okay, in general, we may want to have a different reference system for points in the scene and a different reference system from point in the camera. So in the next slide, I'm going to take this guy here and to add some degree of freedom in order to have more reference system, one for the object, one for the camera. And we are also, what happens in cameras, when you take a picture, what you get is a bunch of pixels. So you have integer coordinates, okay? Here instead, all the reference systems are in meters. So we have also to add a reference system that convert from meter, from metric information to pixel coordinates, okay? So we are taking these 3 pieces and we are going to stick them together. Of course, someone of you also asked me some limitation of this model. Of course, we are working here with a very, very, very simplified model. Okay, we are just taking account of linear effect here. Okay, there is a huge arrays of cameras with different geometries, not only planar sensor, parabolic sensor, or cathode optic cameras. There is a lot of variety. Here we are just focusing on a very simplified special case, which show the geometry we are interested in. So we are not speaking about lens distortion. We are not speaking about non-planarity of the sensor surface. We are not speaking about refraction and other effects as rolling shutter and so on. Okay, so in order to keep the geometry easy and simple, we are just simplifying a lot. But of course, in this way, we have also more portable model that can be adapted to different situations with a certain degree of approximation. So far we have chosen the blue reference frame in the camera center, and we are going to add a reference frame in the center of the image, the green one. And the projection matrix, so the green one is the one that where lowercase m lives. Okay, we have a reference system in a plane, while the blue one is a reference system in the space. Okay, this is the difference. So in general, we can add the red reference frame, which is the reference frame of the world. Okay, and in order to account for the transformation between, and of course we can express capital M either in the reference system of the camera, the blue one, or in the reference system of the world. It's just a matter of roto-translation. So if we add to our model a roto-translation that account for this change of basis from the red one to the blue one, okay, instead of having M, we have R times M plus a translation in blue, okay? And so we can add this to our model. So instead of projecting directly M, we change the basis. So we start with the reference system in the world, and we bring our point in the reference system of the image, and then we proceed as before, just the camera projection matrix. Okay, and what we get, so is that the rotation and the translation that can be encoded compactly in a 4x4 matrix, okay, are called exterior orientation, because they express the position of, basically the position of the blue reference system, which is identified with the camera, with respect to the world reference system. Okay, and we call this transformation as exterior orientation, or exterior parameter, or camera pose and attitude. Okay, and this is just the roto translation that brings from the world reference system to the camera reference system. And it depends on 6 parameters, 3 for rotation, and the other for the translation. Okay, what can be done then is to add another change of basis, change of reference system in the image, because depending on the device, you can have an image with different resolution. So the size of the pixel and so on would affect the coordinate of the image point. And let me absorb also the information about the distance from the camera center to the plane, so the focal length, into this kind of transformation. Okay, and so the general equation here, we have an affinity transformation between the green reference system of the image to the pink reference system of the image. Okay, so you can have a scaling and an offset of the reference system, and in general, so this can be expressed by this transformation encoded in this matrix key. Okay, you have these 2 terms that actually account for how the axes are changed, and an offset in this term here, and also a shear of the camera. Okay, these parameters are called interior parameter. Okay, and actually denotes the sensing device, varies depending on the sensing device you are using, and typically these offset are the coordinate of the image center. R is called the aspect ratio, and typical value is 1, while the S factor is the skew, and the typical value is 0. Okay, so we have added 3 different blocks, 3 different transformations to our perspective equation. Okay, and it will be useful to make this distinction if you work here in as the image coordinate system. So in the image, okay, you have measurements that are actually accessible and are expressed in pixel. If you know the internal parameters of the camera, you can just get rid of this transformation. You can invert this, okay, and work in the, let's say, in the green reference system, okay? But you need to know in advance the camera parameters of the camera. And if you work in the green plane, you are working in the normalized image coordinates, and these coordinates are not accessible if you do not have knowledge of the internal parameters of the camera. And these coordinates are not measured in pixel. They are measured in the unit distance of your world reference system, okay? So their unit is the same as for 3D points. Okay, so if you write down the math, what you have is a matrix of this form. Okay, is a 3 times 4 matrix that can be factorized in this way. You have this 3 times 3 matrix key, which represent the internal camera parameters. And then you have the external parameters, the rotation, the first 3 times 3 blocks, and the translation in the last columns of your matrix. So this matrix has rank 3 because it's a rectangular matrix. So it has most rank 3 because, and has exactly rank 3 because this block here is non-singular. The key for construction, because as determinant is not equal to 0, and R because it's a rotation, so it's an invertible matrix. And the right null space of this matrix is the camera center. Okay, it's the only point for which projections are not defined. Okay, so you can here basically I want you to know that you can express the camera center. So the camera center is completely defined by the camera matrix as the right null space. So you can write the camera center in terms of the columns of the projection matrix. Here you can see why. The camera center can be written in homogeneous coordinate with a 1 at the end. And if you do the math, you can express this as the minus the inverse of the first 3 times 3 blocks of your camera projection matrix multiplied for the last column. And another important geometric object is the optical ray. That was the geometric entities we started with, and can be expressed as a linear combination of the camera center. So we are just writing the equation of a line, so you can keep 2 points, and we choose as a first point the camera center, and as the second point the ideal point of the optical ray. Okay, so why it's an ideal point? How can I see it? Because the last coordinate is 0. Okay, so basically you are taking the optical ray, you are intersecting it with the plane at infinity, you get a point, and every point on that ray can be expressed as the center plus some constant that point. Okay, the ideal point can be seen as their direction. Okay, does it make sense? Okay, now we have a camera model, and to play with camera, the first thing we need to do is to calibrate them. So camera in general, we want to, and all we are going to see is just problem of change of basis. Okay, so determine the orientation of a reference system with respect to another. And camera calibration boils down to determine the reference system, the transformation between the reference system of the camera with respect to some reference system fixed in the world. Okay, and we are going to see 3 kind of method that address 3 different determine 3 different aspects of the camera matrix. So we are dealing with camera resection, which means to determine the whole 3 times 4 matrix. Okay, so the yellow one, the whole matrix, camera resection. Then there are different kind of calibration. For example, you may be interested not in the actually position of your camera, but maybe you want to determine only your internal parameter, okay, of the cameras. So how the geometry of the pixel affect the position between the normalized image coordinate and the image coordinates, okay? And we are only interested in the green part, in the term key, and I'm going to show you a very classic method, which is due to Zhang, the calibration using the checkerboard. And we are also, for some problem, we are also interested in the other part. So the calibration of the camera is known, and we want to determine the attitude, the orientation of the camera with respect to some reference system in the world. So the purple part, the rotation and the translation. And this can be done by using a method that is called PNP. So the first one, and okay, these also, these algorithms are very simple. I'm going to delve in some details just to give you an overview of the math that is behind. And basically the problem is that we are dealing with projective entities. So the problem is that our measurements are defined up to a non-negative multiplicative factor. And this is required to using some technique. And one of the most used in this kind of problem is the direct linear transform. That is a way to solve, let's say, linear system up to this multiplicative factor. Just an algebraic device to get rid of this ambiguity that we have because we are dealing with projective entities with homogeneous coordinate. And the thing is very simple. So we must know in advance some 2D, 3D correspondences. So we typically have a physical object with known quotes. So someone take accurate measurement of that object. Typically, you have a 3D object with orthogonal planes or other phantom that are built for this purpose. And in order to determine the camera metrics, we start with our perspective equation. So what we know is this equation here, okay? You know that the image point can be derived from the projection of 3D points and P by P, okay? But this is known, this tilde here means that this equation is true only up to a multiplicative factor, okay? Perfect. And the trick here is to express this equality in terms of cross product. So in order to express the fact that two vectors are proportional, we can write down that their cross product equals 0. Okay? And that's all. Because if you write this, you are able to constrain from this equation, you derive constraint for your camera metrics. Okay? And here, in other technicalities, we are going to make use of the Kronecker product. So the Kronecker product is just a matricial product that is defined in this way. So you have an M times N matrix and P times Q matrix, and the resulting matrix is the dimension is the product of the dimension. Okay, and you get the matrix by taking this element and multiplying for all the element of the other matrix. Then you take this element and multiply for all the element of the matrix in this way. Okay, you are inflating in some way your matrix, and there's some nice properties. One of the most beautiful one is that the rank of the Kronecker product of two matrices is the product of their rank. And we have this chain of equality. We start from here, and we can rewrite this cross product as in terms of multiplication of matrix by converting basically this guy here as a antisymmetric matrix, taking his entries, and then we can vectorize this equation, and then you have this nice property that if you have the vectorize of AXB, and the problem here is that X is between A and B, so it's difficult to solve for X, which is unknown, is equal to the Kronecker product of B transpose E vectorize X. Okay, so this is nice because in this way you have all the unknown at the right. Okay, so this is actually what we want. This is known, and this is our unknown. So by using this rule, we can rewrite this constraint in this way. So we have the vectorized P, the coefficient of the camera matrix, all on the right, and you just need to solve a homogeneous linear system. Okay, which is very, very easy. And how many correspondence do we need? So how many unknown we have? We need to estimate a 3 times 4 matrix, so 12 unknowns, but we have also a multiplicative scale factor that we can get rid of. So basically we have 11 unknown. The rank of this guy here is 2. Why? Because he's the Kronecker product of a rank 1 by a rank 2 matrix. So every correspondences, so this is what we know. Okay, every known correspondences 3D 2D give us 2 equations. Give us 3 equations, but the rank is 2, so actually only 2 provide a linear independent constraint. Okay, so basically by having 6 correspondences, 6 known points, we can fully calibrate the camera. So we can recover the parameter of our projection matrix. Okay, there is a note that the point must be not non-coplanar. Okay, in order to have this matrix, if you stack all the correspondences in a coefficient matrix E, okay, you have to check the rank of that matrix, and if the null space is 1, you get a solution. Okay, in general, the correspondences are noisy, so you have to solve the system in a least square sense, for example. Okay, how can be done? SVD, and you are happy, you get your solution. Okay, so what we have done, we have minimized, basically, we have solved a linear system, an homogeneous linear system, by having the correspondences between 3D points and 2D points. Okay, we have, in some sense, we have minimized an algebraic error. We have solved a system in this way. Okay, this constraint is just because the system is homogeneous, so we do not want a trivial solution. Okay, and in the problem we are going to see today, is better to minimize a geometric error because it's more meaningful if you have some physical meaning that you can provide to your entities. And what is the best geometric error we can have here is just the geometric residual between the projection of the point and the measured image coordinates. Okay, what we have, what is the drawback is that here we have a nonlinear function to minimize, but you have to use some solver, some Gauss-Newton method to solve this equation. So the standard approach is to we are going to follow is to derive some constraint on our geometric object. Derive by using DLT or something similar, minimize some algebraic error. So get a closed form solution. Then we feed this closed solution as an initial guess to some nonlinear minimizer, which minimize a geometric error, which is more typically provide more accurate results. Okay, so this way allow you to recover the internal parameter of the camera, and the external parameter of the camera mixed together. Okay, because you recover the matrix P, all its entries. Okay, and as long as the camera does not move, the calibration holds. Otherwise, you have to recalibrate your device. And this method is not optimal because we are not enforcing the orthogonality of the first block of the camera, but it provides accurate solution. And once you get your camera metrics, there are some technique based on QR factorization that allow you to factorize your camera, so to recover the intrinsic and the extrinsic parameter. Okay. So what can I do if, so this method works if the calibration object is non-coplanar, okay? What can I do if the object I have is planar? Let's see how the perspective equation changes in order to get an answer to this question. So imagine that without loss of generality, you can always choose that a plane in the scene, and you can assume that your points lie on that plane, okay? And assume that the plane is z equals 0. What happened to the perspective equation? You just get rid of this column here, because if you get the row column product, you see that this column vanish. And basically, you have here an invertible 3x3 matrix, which is an homography. Yes. So you have, and it makes sense actually, because we are just doing something we have done before. So you have all your points that lie on a plane, okay, the blue one here, and we build our homogeneous coordinate in order to make the projection, the central projection, a bijection between plane. So it makes sense that this actually is an homography, okay, something we can expect. And in general, homography, this image is here to express this concept that if you have two images of the same plane, so the homography is the relation that that exists between a plane in 3D and the image of that plane, okay? But is also the relation that exists between two views of the same plane. Because imagine to have the pink plane in the scene. Then you take a picture with the green camera here, and the relation is an homography, okay? You get another picture with the left camera, and the relation is an homography. But homography determine a group, so you can make composition, you can invert homography and make composition. So we can start from this plane, invert the first homography, and then compose it with the second homography. And we have a relation between this plane here and this plane there, okay? And this relation is described by an invertible transformation. And you can see that here points with the same color basically are described by the same homography. Different planes, of course, in the scene will be described by different homographies, okay? Okay, and how homography, so is a mapping that relates two images, okay, two planes. And it's very similar to what we have done before. So if we have enough correspondences, so we know which points is mapped where, we can compute the homography between two images or two planes, let's say, the image plane and the plane in the scene. What is the problem? The problem is that homography are defined in projective planes. So the equations are defined up to a scalar multiplication, but you know how to get rid of that scalar using directly linear transform again. So exactly the same trick we have seen before. You can write this equation before. Here you have a 3D point, and here you instead of this guy you have P, but the trick is exactly the same. You write here this cross product that you want to be 0, and then use the trick we have seen before about the Kronecker product. Okay, in order to, again, here the quantity we are interested is here between the known measurements. We want to move this unknown to the left. Just use the Kronecker product and you are done. Okay, what is the rank of this matrix? Again, the matrix, the rank of this matrix is 2. So we need at least 4 points to have to determine the null space of this in a unique way, the null space of this matrix. Okay. Of course, since correspondences may be noisy, you can use singular value decomposition to solve the system in a square sense. Okay, is it clear for all of you? Okay, perfect. So what we have learned is to, given two images of a plane with known correspondences, determine the transformation that relates these two images. Okay, perfect. Now, suppose that you want to calibrate a camera. So how was born this matrix? This matrix was born by assuming that the plane had the third coordinate equal to 0, okay, and by writing the perspective equation. So let's write exactly what the camera matrix looks like by isolating also the internal camera parameter. Okay, you have this guy here, and the first two columns are rotation, the columns of a rotation matrix, and then you have the fourth columns of your camera projection. Okay, perfect. So what is the idea is that if we have enough correspondences, okay, we can compute this guy here, which is just an homography, okay? And then we have to remember what is the meaning of the first two columns of that matrix, okay? Because we know something about the columns of a rotation matrix. What is the property they satisfy? They are orthogonal and they have unit vector. They have a unit norm. Okay. So the idea is that it is possible to compute this guy here, the homography, and then extract the information about the rotation, the translation, and the internal camera calibration. And this is exactly the idea of the Sturm-Maybank-Zeng calibration. So for each image, we can compute the homography, okay, and we get two constraints on a geometric object that is this matrix here in blue. Okay, the first constraint is that R1 and R2 are parallel, okay, and we can just write the first rotation matrix in terms of the first column of the homography and the unknown internal camera parameters. And the same can be done for the second guy here. Okay, if you write the orthogonality condition, you can see that by doing the math, you get a relation that involves some known entities, the columns of the homography that we are able to estimate, okay, and this guy here. By doing a similar thing, by enforcing that the norm is 1 for R1 and R2, we get another constraint. And so we can solve having enough image, so having enough homographies, we can put constraint on this matrix here, B, which is a symmetric matrix that depends from the internal camera parameter. And once we have estimate this matrix here, in practice, we can retrieve the internal camera parameter, okay, using Cholesky factorization, basically. And once we have the internal camera parameter, we can, of course, also recover the rotation and the translation vector. Does it make sense? Okay. What this calibration gave us is that basically the calibration allow you to measure angle between optical rays. Okay. In fact, if you consider, let's assume that the word reference system is fixed in the camera reference system. Okay, so the metric specialized to this. If you take a direction, a general direction, you can you have this relation. If you multiply a point that lies on an optical ray for the matrix, you get the image point equals the camera calibration matrix times D. And by inverting it, you have that the direction is given by the inverse of K applied to X. Okay, and if you have two optical rays, you can just measure the angle by using the relation we have seen before. Okay, so here I'm just writing D1 and D2 in terms of their inverse, in terms of the inverse of the camera calibration matrix and the point in the image. Okay, so if whenever K is no, you can measure the angle between optical rays. And the nice thing is that here is one of the friends we see at the very beginning, because actually that guy here is the image of the absolute conic. Okay, so there is a relation between the camera calibration parameter and the image of the absolute conic, that, if you remember, played the same role of the conic dual to the circular point that allow you to measure angle between lines. Okay, so something that makes sense. The conic, the image of the absolute conic, is a geometric entity that lives in the plane at infinity, that is preserved by similarity transformation. So its knowledge is equivalent to measuring angles, having angles between optical rays. Okay, so basically the things is that the Sturm-Maybank-Zahn calibration is just a way to determine the position of the image of the absolute conic, if you want to express it in some geometric way. So as we did before, that we identify the image of the dual conic to absolute point to measure angle between lines in image. Here, by identifying the image of the absolute conic, we are able to measure angle between optical rays. Okay, and this is just the algebraic the Sturm-Maybank-Zahn calibration is just the algebraic derivation, and this is just the geometric interpretation of what's happening. Okay. Perfect. And now just an overview of the perspective endpoints problem, which is related to the camera calibration, and assume that the internal camera calibration is known. So the input consists in point correspondences and the intrinsic parameter, and the output is the exterior pose of the camera. Okay, and so for simplicity, here what we have let's analyze this drawing. You have, so what you know. You have known position of 3D point here, okay? And then you have known position of points in the image, okay? But if you know also the camera calibration, you can associate to each of these points an optical ray, okay? A direction, okay? And basically what you want to do is to determine the length of this segment here, okay, and then solve for the orientation that brings the endpoints of this segment to the 3D, to the known 3D points. And the idea so is this one. Consider, for example, the only 3 points, and you have a tetrahedron whose vertex is the center of the camera. Okay, and then you have known ray direction here. Okay, and the first step consists in computing the length of the projection rays, and this can be done just very quickly the sketch of the idea using the law of cosine, because you know the angle, you know this the length of this segment here, because you know the position of the 3D point. Okay, and so you can, by solving this equation, you can determine the length of this segment. Of course, there are some ambiguity in the solution, because the problem is not fully determined, and you can basically you can imagine to have this point, and you can shift this point, you can move this point along the optical rays by keeping fixed the length of the triangle. Okay, and you can do it for every vertex. So you have 4 possible solutions. Okay. Okay, no problem. We just use an additional point to verify. So a 4th point to verify which is the correct configuration of points here. And then once you have determined the length of the segment, you have the endpoints of the segment here depicted as the dashed circle, and you have three of these points, and you have just to compute the auto translation that bring those 3 points in the known 3D position. Okay, so this is the idea of the perspective 3 points problem. Okay, so to sum up, we have seen 3 different three different camera calibration problem. The resection via DLT, that is suboptimal because that does not enforce that there is a rotation. There are better alternatives, and requires 6 points in general position. Then there is and also the other problem with DLT is that it's quite difficult to have a well-done 3D calibration object. So it's easier to have a 2D pattern to calibrate your camera. And in this case, you can use the second method we have seen, that is based on the image of the absolute conic. And you must use at least 3 non-parallel planes, because you have seen that what mattered was the rotation. So it must be must be linear independent, the constraint that can be derived from the homography. And the PNP problem is the other solution, but require that the camera internal parameter is known. Okay. And the other advantage of this solution is that it uses a minimal number of points. Okay. Any questions so far before going into the two-view geometry? No? Perfect. So far we have seen what can be done using a single camera. For 2D, we have an intrinsic ambiguity, so we cannot determine the position of the scene. We cannot infer the structure of scene from a single image without additional constraint, but we can exploit multiple views of the same scene to infer some more information. And we are going to see basically two kind of constraint, and we'll concentrate on the case of two cameras, which are going to be used by Federica this afternoon. And the first constraint is for uncalibrated views. So for a camera matrix for which the internal parameters are not known. And we are also going to see what happens if the internal camera parameters are known. In this case, we have the essential matrix, which is something very similar. So the uncalibrated setup is the geometry relating, describing the uncalibrated setup is called epipolar geometry. Okay. And basically, the situation is this one. We have two cameras, two image plane, and a 3D point. Okay, the 3D point is projected into image in the two different planes. And what happens is that there exists some kind of relation between the coordinates of these 2 points. So the coordinates of these 2 points must satisfy a quadratic relation between the two views. And now we are going to see how this thing works. So pair of points that are image of the same 3D points are going to be called correspondences or matches or corresponding points. So the stage, let's prepare the stage for the epipolar geometry. We need two camera center. The two camera center define a segment which is called baseline. This one, okay? This one in blue. Okay. Then, if you take an image point, a 3D points, you can define a plane. You have the two camera center and the 3D point. These three points define a unique plane, which is called epipolar plane. This plane have an intersection between the image plane. Okay, the image plane and the epipolar plane have an intersection which is a line, and this line is called epipolar line. You have the left epipolar line and the right epipolar line. Okay, and the intersection of the baseline with the image plane, the two image plane, define a point which is called the epipole. Okay, perfect. Let's see if what happened in some particular cases. So what happened if the baseline is parallel to both the image plane? What happened to the epipoles? The epipoles are located at infinity. Okay, and what happened to the epipolar lines? It happens that the epipolar lines are parallel to the axis of the camera. Okay, and another configuration which is interesting is when the camera is moving forward. Okay, in these cases we have that the epipoles. So the camera is moving forward without rotating. Okay. In these cases, the epipole have the same coordinates, and the epipolar line are, let's say, like a radial field that expand from the epipole, that also called in this is called the focus of expansion in this case. But let's focus with the, so just to see that this general configuration specialize in several interesting configuration. Let's stick with the general general case, and let's determine the epipolar constraint. So the two-view relation, quadratic two-view relation I was speaking about. Let's start in this way. So let's consider a point in the first image. Okay, and now let's write the optical ray. We did it before. So we take in order to write the optical ray, I take the center of the camera and I take an ideal point, this one, okay? Which is, if you don't believe me, just take the camera projection, multiply P for this guy here, and you can see that what you get is exactly the coordinate XL. Okay, because this block here times the first 3 times 3 block of the matrix get the identity. Okay. Okay, perfect. Now what we have to do, we know that the image of the image of this point here in the second image must belong to this optical ray. Okay. So we just project every point in the optical ray in the second image. And in order to do so, we just need to multiply the optical ray, so this guy here, for the camera, the second camera. Okay? Which is this equation here. Okay? Second camera multiplied for a general point on the optical ray. And what you get is that this guy here is the projection of the center in the second view. So is the epipole, is this guy here. So this becomes the epipole. And then you get, by expanding this equation, you get this thing here, okay? So in general, a point in the second image, the corresponding point must lie on the line defined by the epipole and the image of this ideal point here, okay? And we can write this equation in a more elegant way. So you are saying that this point can be written as a linear combination of this guy and this guy. So the white point can be written as a linear combination of the green point and the yellow one. Okay. But this means that if you take the line that passes through the green point and the yellow one, okay, this point white must belong to this line. How can we write the equation of this line using the cross product? So if you write the cross product of the epipole for this point yellow, this is yellow point here, you get the equation of the line. So the fact that XR belong to this line can be written as the inner product of the coordinate of XR and the coefficient of the line. And this is exactly what is written here, okay? So you get the epipolar constraint. So you get, if you call this guy here as F, this guy here is called fundamental matrix, so this guy here, okay? And the fundamental matrix is just a 3 times 3 matrix that associate this point here with this epipolar line here. And the incidence relation, so the fact that this point belongs to this line, can be written in this way as a bilinear form, whose entries are involve basically only the projection matrix and the location of the epipole in the second image. Okay, so we have a point line relation between the first view and the second view. Does it make sense for all of you? Any questions so far? Okay. So the fundamental matrix is the unique 3x3 matrix that satisfy this relation for all pairs of corresponding points. Let's see why this matrix has rank 2. So the first observation is that by varying the position of the points in the 3D, we get a pencil of planes that passes through the baseline. Okay, perfect. And this pencil of planes determine a pencil of epipolar lines. Okay, so basically all the epipolar lines passes through the same point, which is the epipole. Okay, and these provide. This is a reason why we have a rank 2 constraint, because if you take a general point, so if you consider an epipolar lines, by varying all the points in the left image, okay, you can see that the epipole lie on that epipolar lines. So since this condition must be satisfied for all the possible XL, this implies that this ERF equals 0 always. So F must not have a trivial null space. Okay, so F is not full rank because you have that the left null space is not 0. Okay, so this is an algebraic and geometric intuition of Y as a rank 2. A second way to see it is that the fundamental matrix is written as the cross product of two points, and since in order to express the cross product in a matricial way, you are using an antisymmetric matrix which has rank 0. That is yes, whose determinant is 0, and from the Binet theorem you can factorize the determinant of the fundamental matrix in this way, and since this guy is 0, also the determinant is 0. So this is an algebraic reason. And a second way to understand why the fundamental matrix has a rank 2 is that is point line correspondences, but the things is that all the points that lie on the same epipolar line return the same line. So the matrix is, the relation is not invertible, because the blue point, the yellow point, and the purple point gives the same epipolar lines. So it's not a bijection. Okay, so it's not full rank. How can we compute the fundamental matrix? So the fundamental matrix can be computed from point correspondences. Of course, sorry, in this slide, we are just saying that there is no, you can choose the first image and the second image, and whenever you want, just use the transpose of the fundamental matrix, and you get the same relation. Okay. And here is an example of what the fundamental matrix looks like. Here we have two images taken from a still camera of two moving objects. Of course, you can also have a scene that is fixed, and you can move the camera and the situation remains the same. Okay. And here you have some corresponding points and some epipolar lines drawn. And you can see that the epipolar lines are not parallel. Okay, here because the motion that the biscuit box is performing is not parallel with respect to the camera axis. How can we compute the fundamental matrix? We have several ways to do it, and first one is to use the 8-point algorithm, which is called here because you need 8 points. You get 8 points of 8 corresponding pairs. You get this relation. Again, you can use something similar to the trick we have seen before, the very same thing. We have two unknown guys here and the unknown here. You can use the Kronecker product in order to isolate F, and you build this system, which is again is an homogeneous linear system that can be solved in a least square sense if there is noise in the corresponding measurement. What you get is a matrix, okay? And do you think you are done if you do this? No, because we have not any guarantee that what we get here, so we get a vector, okay? 9 by 1 vector, F. Okay, we can arrange this vector in a 3 times 3 matrix, but this is not a fundamental matrix, because we see before that an important property of the fundamental matrix is that it has rank 2. So you must force the fundamental matrix to have rank 2, otherwise all the epipolar lines do not meet in the same point. Okay, so the geometric meaningful configuration is when the fundamental matrix is rank deficient. So what you must do is to take this matrix and just compute the SVD and put to 0 the smallest singular value. Okay, this is the best approximation in Frobenius norm of a rank 2 matrix, of a general matrix. Okay, what's also a good practice is to always normalize the point, normalize the correspondences before computing the solution, because since we are using homogeneous coordinate, we will have the first 2 elements that have, let's say, the scale of the image, and the last element is always 1. Okay. This may produce inaccuracy when solving the system. So what is done is just to rescale all the points in order to have to be centered at 0 and to have a radius of square root of 2. And this is not something that we cannot do, because we are just estimating a projective element. Okay, so if we just perform a transformation, as long as this transformation is a projectivity of the input, we can get a valid solution. Of course, at the end, we have to retransform reapply the inverse transformation we have done to the image correspondence. So start from the image plane, transform the image plane in a different way that produce accurate result, compute the fundamental matrix, and then apply the transformation again in order to shift your fundamental matrix to your original plane. Okay, a geometric interpretation. What's happening is you can rewrite. So imagine to have instead of reasoning on the 2 coordinates of the images separately, you can just stack the coordinate of your first image and the second image together. Okay, the relation of the bring by the fundamental matrix is a quadratic relation. So in that space, because you have the transpose of the first vector and multiply by some matrix here, multiply by the column collecting all the entries of the second vector. Okay, and this, if you remember, is just what we did for the conic. Okay, but here we are in a 4-dimensional space, so this is just a sketch to get an intuition. But what you are doing is to fit to your measurement a cone in a 4-dimensional space, and the vertex of the cone, so the singular point, correspond to the two epipole in the 2 image. Okay, so we are just fitting some geometric primitives to some measurement when we estimate a fundamental matrix. Okay, and another popular algorithm is the 7-point algorithm, and the idea is that instead of enforcing the rank 2 constraint by projecting via SVD the matrix we get at the end, we can just take 7 correspondences instead of 8, and then we have a bigger null space. So we have 2 possible solutions. So the solution of an homogeneous system, the space of solution of a homogeneous system is a vector space. Okay. If the rank of the matrix is not full, but you have the null space with dimension 1, you have a single vector that defines your solution. If the null space has dimension 2, you can choose a basis in the space of your solution, and in this case, you can choose two elements of this basis, this one and this one. Okay, and then you can look into that space for that fundamental matrix that has determinant equal to 0. Okay, so basically you write your general solution in this way by using this coefficient, and by imposing that this guy has determinant 0, you get a third-degree polynomial in mu. Okay, that can be solved in closed form, and you get 1 or 3 real solutions. And this is the idea behind the 7-point algorithm. What is the problem? The problem is that you are only enforcing that the matrix has not full rank, but you want to enforce that the matrix has exactly rank 2. And there are some work that study what are the conditions that correspondences must satisfy in order to automatically determine this condition, and there are some configurations that are critical and must be avoided in order to have a working 7-point algorithm. So the fundamental matrix is general, is always defined, but the cases in which the 3 B points are on a plane, because in that case we already know that the relation is described by an homography, so we must use a different model to describe correspondences. In the case there is no translation, again, the model is an homography and can be easily derived algebraically. And there are also some configurations which are unlikely to happen, but exist, for which, let's say, it's not possible to determine the fundamental matrix in a unique way. Okay, there are some configuration of points and some configuration of cameras, for which there are multiple fundamental metrics that describe that configuration that are not equivalent that are not projectively equivalent. Okay, and in practice, these boil down when both the camera center and the 3D points lies on certain surfaces, quadric, second-order degree surfaces. Okay, and what happens is that near these critical surfaces, the solution is unstable, but they do not happen very often. Okay. Again, the approach is to, so far, we have just retrieve fundamental metrics by minimizing an algebraic error. We have solved a system. What is better is to minimize a geometric error. A possible geometric error is the distance between every pair of corresponding points and their corresponding epipolar lines. And there are also some other possibilities. So you can minimize the algebraic distance. You can minimize the symmetric epipolar distance, so the distance between a point and its epipolar line. And there are also some approximation that works very well. One of the most used is the Samson distance, that is the geometric distance to a first order approximation of the curve defined by the fundamental matrix, and also the reprojection error that can be thought as the distance of the point from, let's say, the epipolar cone we have seen before. The best practice is to use the the Samson distance as long as the residual, so the distance are small, but this distance suffer from instabilities near the epipole, as you can see here. This member is not defined when you get here the left epipole and the right epipole. Okay, so these may suffer from instabilities. So it's always a good practice to use also the geometric distance to verify, so the symmetric epipolar distance to compute the residuals. And to conclude, I will also to present a different way to derive the constraint on fundamental metrics. That is this one. So let's start by perspective equation. So you have that the image points are linked to the 3D points by this equation. Just apply the perspective equation to the 3D coordinates. And of course, this equation is true only if you account for a projective depth. So basically you express the scale factor on the left. Okay, if you stack all these equations in this way on this system, your problem to reconstruct the scene is equivalent to solving this homogeneous system. So what is known are the projection matrices and the image point, and what is unknown is the 3D position of the points and the projective depth. Okay, in order to have a solution, so this is just a different way to write this system of equation. Okay, nothing more. In order to have a solution, non-trivial solution, this system must not have full rank. Okay, so by asking that L is not, and this is a square matrix because here you have a 3 times 4 matrix. This is one column and this is one column. So it's a 6 times 6 matrix. Okay, so it's square. So in order to have a non-trivial solution, the determinant of this matrix must be equal 0. Okay, and what happens is that when you write this determinant, you get a condition that involves the camera projection coefficient and the image coordinates, which is exactly the fundamental matrix. So this is a machinery that allows you to write down also multi-view relation, other multi-view relation between multiple images. Of course, you have to add the row to this guy here. So if you have another image, you must add P3, 0, 0, x3, and add another projective depth. The system is not more square, but you must enforce that there are non-trivial solutions by tasking that the determinant of the larger submatrix have null determinant. And this provides you multi-view relation. And the multi-view relation of order 3 for 3 images is the focal tensor, then there is the quadrifocal tensor, and so on. And they can all be derived by writing down these kind of equations. Okay, of course, this is something that Federica is going to use in the afternoon. Once you have a fundamental matrix, you can retrieve the camera projection matrix from them. And this operation, however, is defined only up to a homography in the projective space. So the camera matrix you get are defined only up to an homography of the space. So basically, you get the cameras, you apply an homography that bring the camera somewhere else, okay? And these other 2 cameras give you the same fundamental matrix. So the factorization of the fundamental matrix is not unique, but you can have a, let's say, canonical decomposition that fix arbitrarily the reference system of the first camera in the origin and in the identity, 1, 1, 1, 0. So by choosing the first camera in this way, identity and 0, so basically fixing the reference system in the origin for the first camera, by choosing the origin as the center of the camera, basically, you have a unique way to define the second camera by using only the epipole and the coefficient of the fundamental matrix. And there is an analog of the fundamental matrix for calibrated views, which is the essential matrix, that basically instead of working in the image plane, okay, you know the camera internal parameters, so you can work in the normalized image plane, and everything applies as before, okay? So when you have the camera internal parameter, work in the normalized image plane, and what you get, if you just do the 8-point algorithm, what you get is the essential matrix, okay? And however, the essential matrix is an entity that is related with the calibrated camera. So calibrated camera bring you more information because you can measure angle, okay? So you have also more information from the essential matrix. Basically, here you have a characterization of the essential matrix as a product of a non-zero skew-symmetric matrix and the rotation matrix. The skew-symmetric parts encode the translation between the two cameras, and the rotation matrix, the rotation between the two cameras directly, okay? And also the essential matrix has the property to have determinant equals 0 and 2 equals singular value. So as this kind of characterization. And if you have this kind of characterization, you can, these are equivalent, you can recover a rotation and the translation matrix from the essential matrix. And basically, for essential matrix, you have fewer degree of freedom to recover in the cameras. So for the fundamental matrix, the cameras are defined up to an homography of the space. For the essential matrix, you have fewer possibility. You have actually 4 possible factorization of the essential matrix. That, but only one here is consistent with the fact that 3D points must lie in front of the camera. So by using this information, you can disambiguate between these 4 possible configuration and recover uniquely the essential matrix that describe the relative position of the two cameras. Okay, so basically the idea is that when the cameras are calibrated, you can compute the essential matrix, and the essential matrix, the parameter of the essential matrix store the information about the relative pose between the two cameras, the rotation and the translation. Okay, and there are also other algorithms to determine the essential matrix. For example, 8-point is not the minimal number of points you need, because the fact that the essential matrix has that particular structure, so determinant equals 0 and 2 equals singular value, brings more constraint that can be used to determine the essential matrix, and you can use only 5 correspondences. Basically, you have 5 epipolar constraints given by 5 correspondences. Then you have the singularity condition and a constraint that enforces that the 2 first singular values are equal. And this allows you to characterize completely the essential metric from 5 points. And basically, this algorithm is due to Nister, and is the one that is used most used actually. And the idea is that you have to do some algebraic manipulation as before. You parameterize the solution, okay, the space of solution of all the possible essential matrix compatible with the 5 points correspondences. Then you, so, and this is this guy here, okay? So you have a space of solution which is spanned by 1, 2, 3, 4 vector, okay? 4-dimensional space of solution. Then you write some algebraic constraint that encodes the singularity condition and the fact that the two singular values are equal. And this boils down to solve a 10-degree polynomial that can be solved. And then you back substitute the roots of this solution and recover the essential matrix. Okay, so just to say that there are other possibilities. What can be done when you have the essential matrix and the fundamental matrix? Once you have recovered the position of the camera and you have corresponding points, what you can do is just to triangulate the point. Okay, so you know the point, you know the camera center, you can compute the optical ray, and it's possible to see that in this very simplified setup, this can be done very easily. It's just a matter of similarity triangle, because the triangle composed by this small triangle here and this one, actually is this one, relates to the difference of the coordinates of the points, the pair of corresponding points in the image plane. And what you want to know is actually this length here, okay, that can be computed from this here, this length here and this length here, okay. And in general, you have to solve an intersection problem. So you know the camera, you know the point correspondences, and you might express that the image point are proportional to the projection of the 3D points, okay? And by doing so, you can just recover the 3D point position. Okay, if you have two conditions of this kind, one for the left camera and one for the right camera, you can stack together in a system and solve for capital X, okay? And this provides you an algebraic solution to the intersection problem that, of course, can be refined geometrically. Okay, and the idea, this is also something Federica is going to tell you more in the afternoon, is the idea is to minimize a reprojection error. So the difference between the projection of the 3D points and the measured coordinate in the images. So to sum up, the important things are that you can calibrate the camera. If you know the internal parameter of the camera, you can compute the essential matrix, either with the 8-point algorithm or the 5-point algorithm. The essential matrix can be factorized in a rotation and in a translation, and you can use the rotation and the translation to instantiate the camera matrix and to triangulate points. What happened, the important things to notice is that the reconstructed model is only up to a 3D similarity. So you don't get metric information by this kind of algorithm. And the situation is even worse if instead of using the fundamental matrix, the essential matrix, you use the fundamental matrix, because in that case, the reconstruction is only not up to homography. So you have even less information, only incidence and things like that. Okay. Any questions so far? Too much to be made now, but if you want, we can speak later. Okay. And so always to sum up, we have see this kind of problem. So the problem of triangulation, you have 2D measurement, and you want, so by structure, we denote the 3D scene, okay? And by motion, we denote instead the camera position and orientation and attitude. Okay, so structure is the 3D scene and motion refers to the cameras. Okay, so if you have the triangulation refers to the problem of having 2D measurement, and if you know the motion, you can estimate the structure. Pose estimation refers to the problem instead of having 2D, 3D measurement to estimate the motion, and reconstruction instead. And this is what we are going to see in the afternoon, is start from 2D correspondences, and you must estimate both structure and motion together. Okay, both the two. And this is what we are going to see this afternoon. And to conclude very, very quickly, so far we have assumed that everything is linear and all the correspondences are clean. Maybe we can deal with some noise and solve a system in a least-square sense. But what typically happens when you deal with visual data is that you have a lot of outliers. So typically all these kind of problem must be addressed in some robust way. So you must be robust to outlier. And in the remaining time, I want you to describe a very standard technique that is using computer vision and in the problem we have seen so far, which is resurgence. So the general formulation of the problem is that we have a set of data in some spaces, for example, pairs of corresponding points into projective plane. In this case, we are working in a 6-dimensional space because we have 3 coordinates for each pair of points, and we want to estimate some kind of parametric model. Some kind of parametric model, I mean a line, a conic, a fundamental matrix, and so on. And here is an example. We have a pair of images. Our data, so our set of correspondences, and the model is a fundamental matrix. Here you can see that you have some good correspondences and some outlier, and our aim is to recover the correct matches. And how can it be done? If you think you have some points that lie on a cone and some points that are not on the cone, and we want to recover robustly the cone. Okay, so instead of you can have some heuristic to reject outliers, but the problem is geometric problem. You can think you can draw line and circle in order to have a better picture of what's happening, and all these kind of problems, estimation problem of geometric pattern, let's say, boils down to this one. So we have to find the best fit to some data, and of course we have to define what the best fit is, and typically we are going to consider some geometric error. Here for lines is simple. We have seen some for the fundamental matrix, and depending on the kind of problem, you have to define your own residual. And so far we have seen the least square solution, which is of course a well-established framework that is due to Gauss. There are some other stories about, but one of the most recognized is this one. Basically, the problem of the time was to determine the position of Ceres, which is a satellite of Jupiter, and to determine the next observable position of the satellite that was occluded by some astronomical phenomena. And so you have some observation, and Gauss was the first to derive the least square framework and was able to determine the correct, basically, trajectory of the planet. And by the way, this is the reason why the well-known library Ceres has this name. What is the problem with the least square? As you already know, is that it's fragile to outlier. Even a single outlier can arbitrarily deteriorate your estimation. And this problem become even worse if you have multiple structure in your data. For example, you are you want to estimate an homography, and you are looking at the image we have seen before with multiple plane. And here, the least square problem, the least square approach cannot work, or you have unstructured outliers, as we see before in the photo of the Goomba. And we can make precise the concept of breakdown, which is the breakdown of an estimator is the proportion of incorrect observation that must tolerate before providing an inaccurate estimate. So, for example, the sample mean has a 0 breakdown point because it is sufficient one single point to break down the estimation, and the sample median instead has a 50% of a breakdown point, because you can change half the point -1 without moving the estimate. So it tolerates more outlier. And a way that is commonly used to reduce the influence of out. So I'm just very quickly, I'm going to give you two possible ways to deal with the outlier. First one is to use M estimator, which are instead of minimizing a quadratic loss of the residual, you can use some kind of different function which downweight the influence of outliers. And these kind of functions are called M estimator. And there are several kind of M estimator. For example, this one, you can see that provides, after a certain threshold, provides a constant penalty terms to the points that are far away to the estimate. This in practice has the effect that your estimation is less influenced by points that are far away. So you are not giving too much importance to the outlier. And the basic framework in which M estimator are used is the iterative reweighted least square, that basically alternate between the estimation of basically you can rewrite the problem of minimizing an M estimator as a weighted least square that can be solved iteratively by updating the weight of your least square problem. But I want to focus on a more extreme M estimator, which is just a binary function that equals 0 for points that lie behind a certain threshold and 1 for points outside that threshold. And by minimizing this function, we want to minimize this function. And we say that it is equivalent to maximize. So, of course, minimizing this function is equivalent to maximizes 1 minus this function, okay? And 1 minus this function is strictly related to the concept of consensus. What is the consensus of a model is the number of inliers. So if you revert this function, basically, you have a function that equals 0 for points that are far away to the model and 1 for points that are close to the model, okay? And instead of minimizing the blue one, we want to maximize the red one. How can we do it? And the idea is to exploit, let's say, a Monte Carlo formulation. And basically, this approach is very popular. It's called Ransack. The idea is to explore the space of all the possible models that describe the data and to select the one which maximizes that function. So having the maximum consensus, having the maximum number of inliers. And basically, in this way, suppose you want to estimate a circle. So you start with the minimum number of points to estimate a model, in this case 3, because we have the circular points as we see before. And you estimate the parameter of the model and you validate your model in terms of the number of inliers. As soon as you find a model reaching the maximum number of inliers so far, you update your so far best model, okay? And you keep the model in this way, having the maximum number of inliers. While then, the important thing is that at the end, you have to refine your model on the consensus set found before, because otherwise you have an estimate which is very biased because you are estimating on the minimum number of points your model. Very simple, very elegant, very popular and very used. There are some things that must be taken into account in order to making this approach work. And so there are some details we must care of. The first one is the number of iterations we must perform in order to get a valid solution. Then the sampling strategy to select the points, and also some tests to assess if a model is valid or not. And also the critical things is the selection of the inlier threshold. So when you design your cost function, it's important to decide where it equals 1 and where it equals 0. And typically this value is related to the amount of noise, but it's not trivial to determine the correct way. And this is strictly related in general to the selection of an appropriate cost function to score the model. So as regard the minimum number of iterations, we can have we can relate this number to the probability of retrieving a minimal sample set which is outlier free. And just the idea. So start with the probability that all, let's E be the probability to have an inlier. So 1 minus E is the probability of B an inlier, okay? And this must known beforehand. Then the probability that all the points are inlier, since are events that are independent from each other, is this guy here, okay, power S. Then that probability that at least one point is an outlier are depicted in red here, is 1 minus this probability, okay, perfect. Then the probability that all the selected set contain outliers is the product, so power M of the previous probability, okay? Okay, we are almost done. Then the probability that at least one of these M set is without outliers is 1 minus the previous probability, okay? And by this formula, we can just ask that this value equals some probability parameter, and by inverting this, by taking the logarithm, we can have a constraint on M that tells us the number of iterations. Okay, and what is the problem is so the probability, first of all, as the percentage of outlier increase, the probability grows very quickly. So a large number of iterations is required. And also the problem is that this estimation is optimistic, in the sense that practically the number of iterations required is even larger than the one predicted by this formula. Why? Because it is not true that a minimal sample set composed only by inliers provide a good estimate. Consider, for example, this example here. If this is the inlier threshold, these 2 points have a residual that is below the inlier threshold, so they are inlier. But since they are noisy, the estimate they provide is completely wrong. So these not count as a good minimal sample set that provide a good model. Okay, so this is why in practice you must account for more points. Another aspect is the sampling strategy that you can adopt that can reduce a lot the number of required iteration. For example, by finding point correspondences, you can assume that points that belongs to the same object are in layers to the same fundamental matrix. So instead of uniformly sampling points, you can add some locality prior and sample points that are close to each other. And there are very recent work that exploit this idea and provide very, very improved performance. Also, another things that must be considered is that not all the configuration provide a valid model. There are some models which are degenerate. For example, if you sample points, if you want to establish correspondences between two views, and you sample points that belongs to the same plane, you get a fundamental matrix that is not well defined. Okay, and in Ransack, this will result in a model maybe with a high consensus, but that cannot provide a fully constrained fundamental matrix. So you must introduce some degeneracy check that helps in getting rid of this kind of situation. Here is just a silly example where you want to fit line. If you find points that are too close to each other, you are not able to determine the correct line. You have a pencil of line that well describe your model. For homography, for example, the same applies when you have collinear points. Collinear points determine a configuration that is not able to fully characterize the parameter of your model. And you have also to perform a sample check. For example, for homography, you have some orientation constraint that you must preserve convex hull or things, for example, to fundamental metrics. The idea we saw for the essential metrics that points must lie in front of the camera applies also for fundamental metrics. So there exists some orientation constraint that must be verified, and if they are not, you can just throw away your fundamental metrics and sample another one. And so in general, these are the main steps. You have to sample the minimal number of points, then perform some sample check, for example, the orientation constraint. Then you get the model. You must generate the model and verify it, so if it is valid or not. And then there is the verification step. So you ask, is the model interesting? And to answer this question, is the model interesting? You must use your M estimator, your function. Okay, for in plain vanilla Ransack, you use your consensus function, which is binary, but you can use also other function. For example, you can use this kind of function with respect to the first one, provide a more accurate weight of points. So it does not treat equally all the points that lie inside the inlier band. So the point that is not discontinuous. So if you are here, you are treated as an inlier, and if you are here, you are treated as an outlier. This is more gentle, and you can disambiguate better between inlier and outliers. This is called MSAC, and there is no reason to not use this kind of function instead of the vanilla Ransack. And there are also other alternatives. For example, sorry? Yes. Yes. You can use also other M estimator which are differentiable, but at this point we are not we are not, let's say, we are just evaluating the model. So it's not at the value. But when you refine your point, of course, then you take advantage of having a cost function which is differentiable. And this happened here in the last part, in the model refinement step. Then it can be important to have a function that is differentiable. Yes, of course. Thank you. And please.
So I have a related question. What's the difference between chi-square and m-stack?
Yes, they are similar. Just different flavor of the function. You can choose whatever M estimator you like. They have different statistical property. So if you know something about the noise of your data, you may choose a different M estimator. But in general, so this is a general framework. You can plug in the M estimator you prefer and use it depending on the knowledge of your data.
So chi-square also has a linear part and flattening of the stuff. M-stack also what is true has a similar.
Yes.
So I wanted to ask what's the specifically the difference? Is it the same or is it?
No, they are different. They are different M estimator, but you can plug a different M estimator in the model verification step. Depending, and how can I choose a different model? How can I choose which function I must use? If I know something about the distribution of the noise in my data, I can use different, they have different statistical efficiency, and depending on the distribution, you can use different M estimator function.
Okay, so what's the difference in the statistical efficiency of the chi-square?
I don't know. I don't know exactly what they are for. I know that depending on the distribution, depending on your data, you can choose. They have different efficiency, basically. Some are aimed at skew distribution, some and so on. Another alternative, and I'm going just to conclude, is to, instead of using that loss function, you can minimize the median residual of a point. So this is least median of square, the median residual of a model. And this approach works if you have less than 50% of outliers, of course, because in that case, the median provides a good estimate, okay? And what is the advantage? The advantage is that you do not have to select the correct inlier threshold. You do not have to guess the correct inlier threshold because you have not to dichotomize between inlier and outlier at the stage of estimating. When you, of course, refine the model on the set of points that are close to your estimate, you must perform some statistical test to split into the distribution of residual, and on the inlier you can refine your model. And to conclude, so this was really just the starting point of robust estimation. There is a very huge literature. There are also work this year, so some new work about Ransack, and there are a lot of different implementation. I would like to point to let's see, Magsack, which an efficient implementation, and also Degensack provide good result, which has some nice degeneracy test inside. And there is also, I think, VSAC, so two framework, USAC and VSAC, which are general purpose implementation of Ransack. USAC has different option, actually now is in OpenCV, and VSAC is designed for two-view problems. So you may have a look at it. So to sum up, many improvements have been proposed. Ransack is very versatile, is agnostic on the percentage of outlier, and has reasonable assumption about your data. You must know the noise of your data. If you are dealing with the multi-view problem, this can be specified in pixels, so a couple of pixels, and so the cons that can take longer than expected. Optimal solution is not guaranteed, but there are other alternatives. So not to conclude this part, some references. We are going to put this slide on the website tutorial. And I want to point out, of course, we just scratched the surfaces this morning. There are books written by experts better than me on multi-view geometry. Arthur Zisserman is the Bible. And you may have a look also at the computer vision of Zaleski that has been updated very recently. And also these kind of problems are addressed by long time before the computer vision community, by the photogrammetric community. So also the book of Forstern, Photogrammetric Computer Vision, provides excellent reference about this topic. And an advertisement coming soon, there is the book of Andrea Fusiello on geometric computer vision, which is a very nice book because he also has some well-written code in MATLAB that you can play with to get familiar with many of the algorithms we have seen today and many more. And I think that's all. See you this afternoon, where Federica give you how all these things can be really applied in practice, and we'll offer also some perspective on some hot topics that are still open fields in the area. Thank you. Dillo tu.
We will meet at 1:30.
Standard approaches to use adjustment. Okay. Thank you.
Geometric error and multiplied error.
Yes.
Okay. So when you can accept geometric error is better than multiplied error, I'm always being kind of confused as to why one is better than the other. Specifically, if you look at the
some reference. Yeah. Quite recently, I think that the difference in energy is the distance of higher. So for small receiver.
okay, that makes sense. I can take a look at that. But even if we specifically at the Epipolar graph, so what we did was we had an equation there where we said the x is was similar to, like, you know, when I don't have the equation open here, but basically we had to do like the cross product term, right? So essentially there's that equation and the cross product equation there. I don't see what the difference is, but all we're saying a cross product is that, you know, if they're parallel, then it's equal to 0. Then when we do the geometric error,
You normalize also, so you refer to the algebraic error, you
example, is more difficult to set the threshold because the unit is not understandable. When you use geometric error, you can reason with pixels, so you can set the tolerance depending on your application. So you can see 2 pixels, 1 pixel. I want to be as accurate as to the projection error. Of course, this is some advantage of geometric error.
It does make sense. So finally, do you have a course on this? Can we teach a course?
No.
No? Right.
Some PhD courses, we have taught some PhD courses.
Yes.
Exactly on this topic.
I see.
Thank you. Yes. Quindi cosa devo fare? Lascio così.
No, aspetta, perché c'era la mail, controlliamo. C'era la mail che diceva
Come va, Fede?
the start link are only valid for 2 hours. Non so
Lascio
se poi
qua?
va. Ma io non mi fiderei a lasciare
Ah,
il
neanch'io. Lo stacco
Non
e
lo
lo
so,
porto via.
decidiamo che cosa fare.
Come vuoi, come sei più tranquilla. Se vuoi posso stare
Beh,
qua.
forse si può
Intanto
tipo,
spostiamo.
interrompere la presentazione.
Sì.
Anche l'audio magari.
Okay, I think we can start. Do you hear us on Zoom? Yes, okay, perfect. Okay, so welcome everyone to the second part of our tutorial about multi-view geometry. In the morning, you saw some basics about multi-view geometry, and now we will go in detail into 3D reconstruction from images. And in particular, we will speak about structure from motion. So I will start with a general introduction to structure from motion with a formal problem definition. And I will speak about bundle adjustment. And then the main part of this session will be a taxonomy of structure from motion methods. And in particular, I will speak about both existing algorithms and theoretical conditions when available. And I will also explain the connection to a related problem, which is called synchronization or averaging. Okay, so let us start with the problem formulation. We consider a static scene, meaning that there are no moving objects in the 3D space, and our scene is captured by multiple cameras, which are located at different positions and with different angles. And these cameras produce a set of images. What we are interested here is the inverse problem, meaning we would like to do a 3D reconstruction from images. And this is the goal of structure from motion. In general, in structure from motion, we speak about two things, as already anticipated by Luca this morning. One is called structure and the other is called motion. By camera motion, we refer to the camera matrices, so the projection matrices in an uncalibrated setting, or the angular attitudes and positions in a calibrated setting. And for scene structure, we refer to the coordinates of 3D points. And the goal of structure from motion is to recover both, so both structure and motion. And usually the starting point of a structure from motion pipeline is a set of correspondences or matches that are image points that derive from the same 3D point. And in this figure, you can see some example of corresponding points. And we will assume during this tutorial that correspondences are given. So we don't deal with how to compute matches. And an important observation is that since these correspondences are sparse, also our final 3D reconstruction will be sparse, because we will be able to reconstruct only a subset of the points that are detected in the images. And so the final reconstruction will be in the form of a 3D point cloud. Before starting, it's important to ask if we can do 3D reconstruction from a single image. And if we use geometry only, then the answer is no, because this is an ill-posed problem. We don't have a unique solution for this problem because we have an infinite number of solutions. So as already explained this morning, for each image point, we have an optical ray that defines an infinite number of 3D points that project to the same image point. And this is why using geometry only, we cannot do a single view reconstruction. However, just as a remark, it is possible to do this if we make additional assumptions, for example, a dataset with known 3D shapes. as another recap of what has been seen this morning, we already know how to solve structure from motion in the case of two images. So if we have enough correspondences and, for example, we have calibrated cameras, then we can follow these steps to do two-view reconstruction. We can first compute the essential matrix from the 8-point algorithm, and then factorize the essential matrix with singular value decomposition in order to get both the relative rotation and translation. And this can be used to create a pair of cameras, where the first is set to the reference system. So it has the identity matrix as rotation and the zero vector as translation. And finally, with known cameras, we can compute the 3D coordinates of the points, so the structure, using triangulation. And as already mentioned by Luca, we can generalize this procedure to the case of three images. And in this case, the fundamental matrix becomes another character, which is called the trifocal tensor. And now we will focus on the remainder of this talk to manage the case of multiple views. Now I will recap some notation that will be used through all this lecture. We use lowercase mij to denote the projection of point j in image I, which is a 3 vector if we use homogeneous coordinates. Then we denote by pi the projection matrix of camera I, which is a 3 times 4 matrix. And if we have n cameras, then I can be from 1 to n. And finally, we denote by uppercase mj the 3D coordinates of point j, which will be a vector of 4 elements if we use homogeneous coordinates. And here we assume to have p points, so j can vary from 1 to p. And the starting point of structure from motion is the projection equation, saying that the image point is equal to the product between the camera matrix and the corresponding 3D point, where this is not a true equality, but it holds up to scale. In a particular case where we have calibrated cameras, we have a specific form for the camera matrix. So we can write pi as the product between the calibration matrix, denoted as ki, and another matrix which is obtained by putting one close to the other, the rotation matrix and the translation vector, which are denoted as ri and ti. And just as a recap, the calibration matrix is 3 times 3, and the same holds for the rotation matrix, whereas ti is a vector of 3 elements. And in a structure from motion, in an uncalibrated setting, the only thing that we know are the image coordinates, whereas both the pi matrix and mi points are unknown. And this is exactly our task. So to recover both pi and mj for all the indices. Whereas in the calibrated case, we know the calibration matrices. So our task is to recover both a rotation and a translation vector for each camera. And this is exactly the goal of structure from motion. So to recover both camera motion and scene structure starting from image points. And in the calibrated case, the pause step reduces to recover both the rotation matrices and translation vectors. So another important observation. In this problem, the solution is not unique. but we have infinitely many solutions. However, we can say that this ambiguity is one single matrix. So the solution is defined up to a global projective transformation. And this is really simple to see, because if we look at our projection equation, we can multiply inside here by a matrix Q, which is a projective transformation, and its inverse. And this can be done because the product is the identity, so it does not have any impact in the factorization. And then we can put this Q close to Pi and Q minus 1 close to MJ. And this is like having new cameras and new points in another coordinate system. In the calibrated case, we have a similar situation, but the ambiguity is a different transformation. We get that the solution is defined up to a global rotation, translation, and scale. And this can be represented in a compact way using 4x4 matrix. Now another recap. Let us see which are the differences between a calibrated reconstruction and an uncalibrated one. So in the uncalibrated case, we have no assumptions, meaning that we have no prior knowledge about the cameras, and our final reconstruction is projective. And as seen this morning, projective transformation, for example, does not preserve parallelism and angles, and this explains the distorted reconstruction that we may get. However, it is possible at the end, so after the reconstruction, to get a metric reconstruction, and this is called metric upgrade. On the contrary, in the calibrated case, we have additional assumptions, meaning that we are required to know in advance the calibration metrics. And this, for example, can be estimated from the checkerboard, as seen this morning. And in this case, we have a metric reconstruction. So we have, for example, a house where parallel lines are parallel and so on. And these are the main difference between the calibrated and uncalibrated case. And hereafter, we will address both cases. So the first approach to solve structure from motion is bundle adjustment. The starting point is the projection equation. And the first idea is to set up a cost function which is based on the reprojection error. So we can suppose to define a distance in the image plane between the left and the right side in this equation. And for example, we can take the square distance. And since we have many observations, we need to take the sum over all the points and over all the cameras. And the optimization variable here are both the camera matrices and the 3D points. And this is what is performed by bundle adjustment. And geometrically, what is done when this cost function is minimized is to adjust this bundle of optical rays between each camera centers and the set of 3D points, or equivalently between each 3D point and the set of camera centers. In general, we can use cost function which has a more general form than the previous slide. So, for example, as the distance, we can use the perspective projection, where we divide the coordinates, the homogeneous coordinates in the image plane by the third coordinate. And as in order to address the case of outliers, we can also apply some robust loss, such as the ones derived from M estimator. And moreover, in practice, we may have some missing correspondences so that not all points are visible in all the images, for example, due to occlusion. And in this case, we put some indicator variable called Wij, that is equal to 1 if point J is visible in image I and 0 otherwise. And once again, we sum over all visible points and over all the cameras. And we minimize over both cameras and 3D points. So in terms of 3D points, the number of parameters is 3 times number of points, whereas for cameras, we have 11 parameters for each camera in an uncalibrated setting, because each camera is 3 times 4, but it's defined up to scale, so we can remove 1 degree of freedom. Whereas for the calibrated setting, we have 3 parameters for rotations, 3 for translation, so we have 6 parameters for each camera. And in addition, we can remove the global ambiguity by fixing one of the cameras. And this can reduce the number of parameters that are involved in this optimization problem. So which is the problem of this cost function? It is hard to minimize it because it's non-linear. There are no closed form solutions, so we can only resort to iterative approaches. And one of the most popular is the Levenberg-Marquardt algorithm. And this is a combination of gradient descent and Gauss-Newton. And the idea is to take the best of both worlds. So that from gradient descent, we get a rapid decrease in the cost function, whereas from Gauss-Newton, we get a rapid convergence in the neighborhood of the solution. And this is what is done by bundle adjustment. Another problem is that this is a really large problem. We have a large number of unknowns. And for example, if we have thousands or hundreds of cameras, then this results in high number of parameters. But the good point is that the Jacobian matrix has a sparse structure, and this can be used to improve efficiency. In particular, there are 2 types of structures. One is called the primary structure, and this is a general structure that holds for any problem, and it derives from the fact that each term in the previous cost function involves only either one camera or a point, but not all the cameras simultaneously. And this is shown in the right figure. Moreover, we may have additional sparsity coming from the fact that some points may be not visible in all the images. And these observations are at the basis of having some reduced system, which simplifies the optimization. In addition to this observation, there has been several efforts in the literature to improve the performances of bundle adjustment, such as in these references. And in terms of software, one of the most popular is the series solver. So why is not used the bundle adjustment as the unique way to solve structure from motion? Because it may converge to a local minima. So in order to work in practice, it requires to be initialized close to the solution. And this is why we do not use only bundle adjustment to solve structure from motion, but it is used only as a final refinement. And this is the main motivation of all the methods that we will see later. So all the methods presented later can be seen as a way to initialize bundle adjustment, but this refinement will be always used at the end. Structure from motion has been researched by many authors over the years, and there are many possible ways to classify existing methods. This is just my personal classification. So here, existing methods are classified based on which subproblem they address first, between motion or structure. So on the left, we have structure and motion methods that consider simultaneously both structure and motion. And in particular, I will speak about incremental structure from motion, which is one of the most popular ways to solve structure from motion, and also projective factorization. That was one of the earliest attempts to address the problem. Then we have what I call the motion first, so a class of methods that focuses on motion only. And in particular, two different approaches belong to this category. One is global structure from motion, and another one is a recent method based on the multi-view fundamental metrics. Finally, I will also briefly speak about a structure first approach, which is in some sense the dual of motion first, because it focuses on structure only. In particular, we will see that it is possible to recover the structure without considering motion. So now we will start with the first category, which is incremental structure from motion. So this is the very general pipeline of incremental structure from motion. As already mentioned, our input will always be correspondences over images. And in this specific approach, we also assume in addition that images are organized in a sequence. So this approach considers structure and motion in a combination, and in particular, it progressively builds an increasing model. And at the end, as I mentioned before, we will refine the solution using bundle adjustment. So this is the main idea of incremental structure from motion. We want to grow iteratively a partial model, which is composed of cameras and points. So we assume to have some initial pair, and with this pair, we initialize our model. Then we process the images in a sequence, and when a new image is added, we update the model. And we proceed in this way until all the images have been considered. And now I will explain more in detail these steps. So first, the first step is how to initialize the model. This is essentially what I reviewed in the first slides. And this is just a two-view reconstruction problem. For example, if we are in a calibrated setting, we use the correspondences in our initial pair, so in two images, we can compute the essential matrix, then get the relative pose from it, and create two cameras. Where the first camera is composed of its calibration matrix, which is known, the rotation is set to identity, and the translation vector is set to 0. And this is the same as fixing our global ambiguity. For the second matrix, instead, in addition to its calibration matrix, which is known, we use the relative rotation and translation computed from the essential matrix. And moreover, since our relative pose is defined up to scale, we need to decide one scale of our translation. For example, we can set it to 1. And this corresponds to fixing the global scale ambiguity. So this is the procedure just to initialize our model. In particular, this was just to compute the camera motion of our initial model. Concerning 3D points, since we know cameras, we can solve a triangulation or intersection problem and get our initial structure. So after this step, we have an initial motion and an initial structure for two images only. Then we add a new image, which is the third one. And the key idea is that since we know image correspondences, which are the blue lines, we also know the 3D points associated with the first two images. Then we can get the points in the third image by using these connections. This means that the information from the first two images is transferred in the third image in terms of correspondence between 3D and 2D points, meaning that we get the red line. And this means that we know the 3D points, the 2D points for the third camera, but not the camera. And this is exactly resection problem or perspective endpoint problem reviewed this morning. So by solving this problem, we can get the camera matrix of the third image. And this means that we are updating the motion. Concerning structure, we can update it using, once again, intersection, using the matrices of all the three cameras and the available 2D correspondences. And in particular, we have two situations. The points that were already observed in the previous images are refined, whereas we may also have some new points that are present in the third image, but not in the first two. And this means that we may add new points to our reconstruction. And this is done for the third image and then is repeated for all the images in our sequence. So since we are alternating between resection and intersection, this approach is also called resection intersection, in addition to incremental or sequential structure from motion. Since it's an incremental approach, we may propagate the error. And this is why in this specific setting, we apply bundle adjustment even at intermediate steps, not only at the end. So just to summarize, we start from correspondences and a sequence of images. Then for structure and motion estimation, we first initialize the model with a two-view reconstruction, and then we update the model by resection intersection. And we also refine the solution using bundle adjustment. So which are the advantages and disadvantages of this approach? In this case, missing data are naturally handled, and so we do not require that all points are visible in all the images. Moreover, this represents the most successful pipeline in practice. However, this is not a global method, so as already mentioned, it may suffer from error accumulation. And moreover, the choice of the initial pair is very important, and it may affect the final results. Concerning the software, one of the most popular systems is CallMap, and it follows the pipeline that I have just explained. Starting from image, the first step, which is not covered in this tutorial, is correspondence search, which produces a set of correspondences over all the images, and then it proceeds with the incremental reconstruction. So starting from an initialization, we add a new image, and it's called by the author image registration. Then 3D points are reconstructed by triangulation. We refine our solution with bundle adjustment, and we may also decide to remove some points based on the reprojection error. And this is called outlier filtering. Of course, this is just general explanation, but implementation details are very important. And in particular, the authors of CallMap proposed several improvements over previous work, and these are just a few of them. One is the next best view selection. So in order to choose the next, which image to add next, they define some score that tends to favor images with more visible points and more uniform distribution over the image. Moreover, they apply bundle adjustment not on all the images, but on a subset of images which are more connected. And finally, they remove redundant cameras that are cameras which are very similar to each other by clustering these similar cameras into groups. And within a group, cameras are collapsed into a single camera. And this permits to reduce the number of parameters and hence improve efficiency. We can also generalize our incremental reconstruction to the case where our images are organized in a tree instead of a sequence. And the idea here is very similar. So if we look at the leaves of our tree, then for each pair of leaves, we solve a 2-view reconstruction problem. Then we traverse the tree, and at each node, we can have 2 possible operations. One is that we need to add 1 image, for example, here. And this is the same as sequential structure from motion. We just perform a resection intersection. Then we may also have the case where we need to merge 2 independent reconstructions, for example, here. And in this case, since we have 2 3D reconstruction, we can view this problem as an example of 3D registration. And this is applied to all the trees, starting from the leaves until the root. And this will produce our final reconstruction. So, now we move to projective factorization. Similarly to structure and to sequential structure from motion, this approach considers both structure and motion at the same time. Yes, here is the microphone.
Could you just repeat again the benefit for the reasons to go with the hierarchical versus a sequential?
Actually, it depends on the data set. If images are taken in a sequence, there is no reason to use a hierarchical approach, whereas if images have a different structure, then it may be beneficial.
Okay.
For any questions, feel free to interrupt me. Okay, so projective factorization is an example of uncalibrated structure from motion. So here we do not assume to know the calibration matrices, but only correspondences. And this method recovers both structure and motion simultaneously. And as always, at the end, we will apply bundle adjustment. This is an elegant method because if we make some specific assumptions, then it can solve the problem in one single step. First, let us rewrite our projection equation in another form. As mentioned before, in general, the projection equation has an equality up to scale, but we can remove this up to scale and put a real equality by introducing some unknown scale for each image point. And these scales are typically called projective depths. With these additional unknowns, we have an equality for our projection equation. So each image point is multiplied by its scale, and this is equal to the product between the camera matrix and the 3D point. Of course, in practice, we don't know these scales, but for the purpose of explaining the method, we will first consider the case where these depths are known. So first, let us consider once again our projection equation, and we observe that we can represent this equation in a very compact form that considers all the points simultaneously. We also make another simplification, so the case where all the points are visible in all the images. And later we will deal with the case of missing correspondences. So we can place each image point multiplied by its scale in a big matrix, which is called measurement matrix. And in this matrix, each column corresponds to a point and each row corresponds to an image. And since each image point has 3 coordinates, this will be 3n times number of points. Then this is just the left side of our equation. For the right side, we do something similar. We collect all the cameras one under the other and all the 3D points one close near to the other. And the first term containing all the camera matrices is also called the motion matrix. And since its camera is 3 times 4, this will be 3n times 4. And the second matrix is called structure matrix, and it will be 4 times p, since we are working with homogeneous coordinates. So if we call the motion matrix P, the structure matrix S, and our measures as W, then we can write all our projection equation as a single matrix factorization. So we have that our measurement matrix can be written as the product of the motion matrix and the structure matrix. And this in particular implies that our measurement matrix has rank 4. So the rank is low compared to its dimensions. And this rank property is the key to projective factorization. So recall that we are assuming that the projective depths are known. So the left side of our factorization is known, whereas the right side are both unknowns. Of course, this factorization holds when we do not have noise, but in practice, if we have noisy measurements, we will not have really an equal in this case, and so in particular, W will not have exactly rank 4. But we can use these rank 4 properties to solve the problem. So we can look for the best rank 4 approximation of our measurement matrix. This means that we want to find our motion matrix and the structure matrix such that the product between P and S is as close as possible to our measurement matrix W. And this is a known problem, and that can be solved in closed form using singular value decomposition. So more precisely, we starting from our measurement matrix, we compute its singular value decomposition. So we will have an orthogonal matrix U, a diagonal matrix with singular values, and another orthogonal matrix V. In order to have a rank 4 matrix, we remove all the singular values from 5 on. So we put zeros here. And then this is equivalent to consider only the first columns of U and only the first 4 rows of V. So at this point, we are close to a factorization of what we required, meaning that this matrix has the same size as the motion matrix, and V, the first rows of V have the same size as the structure matrix. We only need to take care of this 4 times 4 matrix with singular values. But we can view this matrix as our projective ambiguity, which can be put either with motion or the structure. For example, we can put the projective ambiguity together with U, and this will be our final motion matrix. Whereas the matrix containing the first 4 rows of V will be our structure matrix. And this is our solution to projective factorization in the simplified case that we are considering. So all projective depths are known and all points are visible in all the images. So under these assumptions, we can recover both structure and motion in a single step using singular value decomposition. And as always, refine our solution at the end with bundle adjustment. As you may note, these are very restrictive assumptions that are typically not satisfied in practice. And now we see how to deal when they are not satisfied. First, in the case where the projective depths are unknown, we can solve the problem by alternation. So if we assume that depths are known, then as explained, we can recover structure and motion using singular value decomposition. On the other side, if structure and motion are both known, then we can easily recover the projective depths because our projection equation, if everything except depths are known, is a very simple linear system. So we can solve this system to get these unknown scales. So with known depths, we can recover structure and motion. With known structure and motion, we can recover depths, and we can iterate between these steps until we reach either convergence or a maximum number of iterations. And for the initial values, we can, for example, set all the depths equal to 1. Now we see how to do with missing correspondences. And this is an example of a matrix completion problem, because we may see our measurement matrix as an incomplete matrix, because we know some of its entries, which corresponds to some image points, but we do not know all the entries. So some point may be missing in some images. And guessing the missing entries of a big matrix is an example of matrix completion. And the typical approach to solve this problem is to exploit the low rank assumption and recover the missing entries by minimizing the rank or other convex approximations, such as the nuclear norm. And this can produce a full matrix, and from this full matrix, we can then solve the problem as shown before. So some observation about projective factorization. In contrast to the previous approach, this is global, meaning that we consider simultaneously all the points and all the cameras. And in general, a global approach promotes error compensation. Moreover, here we are considering very weak assumptions, meaning that we do not assume the knowledge of the calibration matrix, but we consider the most general camera model, which is the projective camera. As a negative point, these require a lot of memories because we need to store all the points simultaneously. And finally, it's important to mention that there are also some alternative approaches in the literature. One is the variable projection method, where the idea is to rewrite our optimization problem by eliminating some variables. And moreover, it has been recently proposed an approach based on deep learning where an encoder architecture is used. So now we ask ourselves if this projective factorization is a well-posed problem. And unfortunately, without making additional assumptions, the answer is no, meaning that in this problem, we may have some false solutions. And this happens even in the most ideal case where we do not have noise, we do not have missing data. And a false solution is a solution that satisfies the projection equation, so is a valid solution, but it is not projectively equivalent to the true solution. And the presence of false solution means that the solution to the problem is not unique, where we always need to think about uniqueness in the sense of up to a single projective transformation. And here there is an example of a false solution. And for example, by exploiting the fact that the camera center is in the null space of the projection matrix, we can set some, for example, one 3D point to some camera center, and this will be, the product between the camera and the point will be 0, for example, here. And if we have a 0, then we satisfy the projection equation, because, for example, if this product is 0, we can set the projective depth to 0, and our equation is satisfied. So, and this is an example of a false solution. And several examples can be created, such as the one in this figure, where it can be checked that the projection equations are satisfied, but this is not equivalent to our true solution. And in particular, it was observed that false solutions appear only in some specific situations. One is the case where the depth matrix has either 0 rows or 0 columns, where the depth matrix is a matrix that collects all these unknown, all these projective depths. And another case is the case where the depth matrix is cross-shaped, meaning that all the entries are 0 except of 1 row and 1 column that are placed like a cross. And more in general, as can be observed by here, these false solutions appear only if some depths are 0. So one may ask how to deal with this problem. So the good thing is that if we consider some additional constraints, then we avoid the false solutions. So we have a well-posed problems. In particular, if we assume that all projective depths are non-zero and cameras points are in a generic configuration, then we have a well-posed projective factorization, meaning that the solution is unique up to a single projective transformation. And this is the classic projective reconstruction theorem. However, the problem of this theorem is that enforcing depth to be non-zero is a constraint which is hard to implement. And this is the main motivation for generalizing this theorem to a more general setting, which allows constraints which are easier to implement. And this is what is done by the generalized projective reconstruction theorem. So according to this theorem, if our cameras and points are in a generic configuration, and moreover, the depth matrix does not have neither 0 rows, columns, and it is not cross-shaped, then we have a well-posed projective factorization. And this is important because these constraints are easy to implement compared to the constraints that projective depths are non-zero. And these are some examples of constraints that can be placed in some optimization to avoid these false solutions. One is the step-like mask constraints, where we fix some elements of the depth matrix that form some a step-like mask. And this is an example of a linear equality constraints which are easy to implement. Another example of constraint is reported in the right part. We can create some tiles in our depth matrix, and then we may require each tile to have some fixed norm. And this is an example of a compact constraint. And in general, compact constraints are important because they have good convergence properties. So now I will conclude the part of projective factorization with an example of a recent method that incorporates these constraints in the solution. So the idea is to start from an initial subproblem, which is well posed, so it does not have the cross shape form. And then we incrementally add missing tiles, where each tile corresponds either to a view or to a point. And we repeat this until we cover all images, all points, and we get our final reconstruction. In particular, if we want to add cameras, so we have known points, then as already explained, solving for cameras is a linear problem and it's a resection problem. On the other hand, if cameras are known, then solving for points is another linear problem and it's an intersection or triangulation problem. And moreover, some constraints which are compliant with the theorem are used. In particular, the authors of this approach fix the average depth in a tile to 1. And this is another example of a linear constraint. And a linear equation can be viewed as a way to substitute one of the parameters in the system and hence to remove some unknowns, while ensuring that our reconstruction is compliant with the theorem. In addition, in order to prevent error accumulation, after each inclusion, the authors remove outliers using ransack, and they refine the reconstruction by re-estimating all the points and views. So this concludes the part about projective factorization. Are there some questions so far? Is everything clear?
Does CalMap implement the factorization?
The paper of CalMap is about incremental structure from motion. Honestly, I don't know if they recently added also some projective factorization stuff, but I don't think so.
So if you are a lot of memory to factorization, what's your order of magnitude?
It depends on the data set, but you can think that in popular data sets, there are hundreds or thousands of images and thousands of points. So this matrix is really, really big. Okay, so we can start the global structure from motion. Global structure from motion works in a calibrated setting. So in addition to the image correspondences, it considers also the calibration matrices as input. And this is the general pipeline of global structure from motion. The focus of this approach is on motion only. So in the next slide, we will see only how to recover camera motion. And this approach is motivated by the fact that if we know the camera motion, then solving for structure is trivial, as it can be done by triangulation only. And this is why the focus is on motion only. And as always, the bundle adjustment is applied at the end to refine the solution. In this case, we represent our data as a graph, which is also called the viewing graph. And in this graph, each node is a camera, and we put an edge between two cameras or images if we know the essential matrix or the essential matrix of that camera pairs. And this means that we have enough correspondences and hints that these images has some overlap in terms of which part of the scene they view. And in general, this graph can be large and also incomplete, meaning that we do not have all the possible edges, but only some of them, due to the fact that two cameras may view different parts of the scene and hence have no points in common. I said that the focus is on motion only, and in addition, motion is split into steps. First step is recovering camera motion for pairs of images individually. So we have multiple image pairs that represent edges in our graph, and for each pair, we can recover the relative motion of that camera pair. And this is done once again by solving a two-view reconstruction problem. So by decomposing the essential matrix into relative rotation and translation from the singular value decomposition. And this is the first step of motion recovery. Then in the second step, we recover simultaneously all the rotations and translations of the cameras in a global reference system. And in particular, I will explain then more in detail how to address the second step. It's important to observe that in the first step, we have only local or relative information, because each relative rotation or translation involves only two images. So we know the relative rotation of a camera with respect to another, but not with respect to all of them. In contrast, in the second step, we have some global or absolute information, because we are considering not only one edge in the graph, but all the graph simultaneously. And another important observation is that we use corresponding points only in the first step, because they are used to retrieve the essential matrix, but then they are not used in the second step. So in the second step, we work with transformations only, not with points. And this is why we may also call this method a frame space approach. Just to summarize with a figure, the first step of motion's recovery in global structure from motion produces the relative poses between camera pairs from the essential matrices, which are associated to the edges in our view graph. Whereas in the second step, we start from these relative poses and we get our absolute poses, all together with respect to a single reference frame. The starting point of this step is also called the consistency constraint. So we denote by Zij the relative motion of pair Ij which is a rigid transformation between the reference system of camera J and camera I. Moreover, we denote by xi the absolute motion of camera I, which is another rigid transformation that model the transformation between camera I and an external reference system. And the same for camera J. So if we look at the figure, Zij represents the transformation that map reference J in reference I, whereas Xi represents the transformation that maps an external reference system, also called the world reference system, into the reference of camera I. So the same holds for Xj, and this means that the inverse of Xj maps camera J into the world reference system. So we can look at this figure as a composition of transformation, meaning that going from camera J to camera I is the same as going from camera J to the world reference system and then from the world reference system to camera I. And this is exactly the meaning of the consistency constraint. Our relative motion is the product between the absolute motion of camera I and the inverse of the absolute motion of camera J. And this is our starting point. So more precisely, we now give some notation related to these transformations. Our relative motion can be viewed as a matrix of the special Euclidean group that represents a rotation followed by a translation in 3D space. So we may view this Zij as a block matrix, which has a block representing a rotation, Rij, a vector representing a translation, Tij, and then 3 zeros and a 1 in the fourth row. This is what we mean by the relative motion of the pair Ij. And for the moment, we consider it as known, but it is not exactly this way. Then, in a similar way, we represent our camera poses, also called absolute motions. So we may represent the motion of camera I as another SE3 matrix, which has a rotation block Ri, a translation block Ti, and then zeros and one. And the same holds for camera J. And it's important to note that absolute motions are unknown and are the variables that we are interested in recovering. And in particular, this notation permits us to split the motion stage once again into steps. In particular, if we consider our consistency constraint, saying that relative motion is the ratio of the absolute motions, then if we make matrix multiplication blockwise, we can get some formulas of the rotation block and the translation block. In particular, by computation, we get that the rotation block, so the relative rotation, Rij, is the product of Ri and the transpose of Rj. And we get another formula for the translation. The relative translation is minus the product of the same quantity times the translation of camera J plus the translation of camera I. And in particular, the second terms can be further simplified if we multiply both sides by the inverse of the rotation of camera I. And this permits to rewrite the same equation in terms of camera centers instead of translations. So we may think of this as a sort of change of variables. So if rotations are known, then we get that the relative displacement between camera pairs, which is denoted by Zij lowercase, is the difference between the center between camera I and camera J. And once again, here we have splitting our consistency constraint by dividing the rotation component from the translation component. And this is the basis of methods for recovering camera rotations and translations. And in particular, we will start from the rotation component using this formula, and later we will see the translation component. So now we focus on rotations only, and the starting point is the rotation part of our consistency constraint. Of course, our constraints involves 2 cameras only, but we may have multiple pairs of cameras. So we may have multiple edges in our graph. We now collect all these constraints in a single compact form that involves all the edges of the graph simultaneously. And we first consider even here the case where we do not have missing rotations. So the case of a complete graph. We construct this block matrix called capital Z, which has a relative rotation in each block. For example, in the block associated to the first row and second column, we have the relative rotation between first and second camera. In the diagonal, we have the identity matrix. And in the same way, we place all the relative rotations in the correct place. And since rotations are 3 times 3 matrices, this big matrix is 3n times 3n, where n was the number of cameras. And this is known. So this is the input to our method. In a similar way, we may collect all the unknowns in a single matrix called X. In particular, we place each absolute rotation one under the other. So we have the rotation of the first camera, then the second, and so on until the last camera. This will be 3n times 3, so it's a slim matrix, and this is our unknown. So our goal is to recover X starting from Z. In order to do this, we rewrite the consistency constraint using this new notation. So our Z will be the product of X and X transpose. And this in particular implies that Z has several interesting properties. One is that it is symmetric, moreover is positive semi-definite, and moreover it has rank 3. And these properties have been used by multiple authors to produce several algorithms. We start from the simplest way to solve the problem, and then I will also mention more advanced methods. So just as a recall, Z is known, it contains all relative rotations, X is unknown, and it contains all absolute rotations. And one method to recover X from Z is based on the following simple observation. So we may observe that the columns of X are 3 eigenvectors of Z, and the eigenvalue is equal to n. So in formula, this means that the product between Z and X is n times X. And this is very simple to verify because it is enough to write down Z times X and replace Z with the consistency constraint, which is X transpose. Then we may observe that X transpose times X is the sum of or each rotation multiplied by the transpose of itself, but this is the identity since they are rotation matrices. So we are summing n times the identity, and this will produce n times x. So this is the result that is at the basis of a simple method for recovering rotations, because it is based on computing the eigenvectors of our matrix. Before detailing the method, we will consider the case of missing data, where we have some missing rotations or edges in our graph. For example, if we do not have a measure for the rotation between camera 1 and n, then we put 1, 0 in correspondence of this block. So we have a big matrix with some missing rotations, but the result from the previous slide can be generalized also to this case. So also in the case of missing data, the columns of X will be some eigenvectors, but they are not eigenvectors of Z, but of a scaled version of our matrix. And in particular, the scale matrix is a diagonal matrix, which is a replication of the degree matrix of the graph. So D denotes the degree matrix of the graph. So it counts how many edges are present for each node. And the Kronecker product with the identity has the effect of replicating the degree matrix in a diagonal form. And so it can be proved that if we multiply the inverse of this matrix by Z, then we get a similar result as the previous slide. So we get that the columns of X are eigenvectors of this matrix with eigenvalue 1. And it can also be proved that this is the largest eigenvalue. And this is the basis of this method for recovering camera rotations. We have as input our matrix containing relative rotations, and then we scale it according to the degree matrix of the graph. Then we compute the leading 3 eigenvectors. And the fact that the eigenvalue was the largest is important because it allows us to compute only the leading eigenvectors and not a full eigenvalue decomposition. And in particular, in terms of notation, we collect all these eigenvectors in a matrix called U. Then an important fact is that in this way, we are working with general matrices, so we are not really enforcing the constraints of rotations. And this means that we may end up with some blocks which are not rotations. And this means that at the end, each 3 times 3 block of this matrix needs to be projected onto the space of rotations in order to have a valid solution. And this can be done using singular value decomposition, because projecting a matrix into a rotation is a well-known and studied problem that can be solved using SVD. In addition, this has been detailed for the case of missing data, but it is also possible to further generalize it to the case where we have some weights that say how reliable each relative rotation is. And so this can be used to have a robust method which is similar to iteratively reweighted least squares. So a question here is which cost function are we optimizing with this method? So we can start from the deviation of the consistency constraint using the Frobenius norm and summed over all the pairs of images. And of course, in principle, we should minimize over the space of rotations. Then if we rewrite the Frobenius norm using the trace and some computation, we can have an equivalent form where we are maximizing the trace of the product of some matrices. In particular, we are maximizing the trace of X transpose ZX. Then at this point, we consider our relaxation, which means that we ignore some constraints and consider only a subset of the constraints, and this produces a simpler problem. In particular, we only enforce the column of our optimization variable to be orthogonal. And this is equivalent to maximizing the sum of three quadratic form, and this is known as a Rayleigh problem, whose solution is given by the leading eigenvectors of our input matrix Z. So to summarize this slide, if we start from a principled optimization problem to solve for rotations, then if we ignore some constraints and consider a simplified problem, then we get our spectral decomposition. So the spectral method explained in the previous slide is solving a relaxed version of the original optimization problem. And of course, this is only one example of a relaxation, but there are also others in the literature. And for example, another case is the semi-definite relaxation, where the input matrix with all relative rotations is enforced to be positive semi-definite, and all other constraints are satisfied, are not enforced. And another example is the rank relaxation, where only the low rank property is enforced. And to recall, our Z matrix has multiple properties, so it's symmetric, positive semi-definite, low rank, and made of rotations. So these methods are focusing only on one specific property to develop a specific optimization problem and a solution. More in general, another cost function can be considered. We can, instead of the Frobenius norm, we can consider a generic distance defined on the set of rotation, and consider once again the deviation between the relative rotation and the product of the absolute rotations. And for example, popular distances are the angular distance or the distance between quaternions. And we may also consider some exponent like 1 or the square for each term in this distance. We need to sum over all the edges in our graph. And as always, in principle, we should minimize over rotations, where rotations can be parameterized in several ways, like rotation matrices as done before, or unit quaternions, or also the angle axis representation. However, in general, this approach is not used in the sense that direct optimization of this cost is very hard, because it was proved that this is a non-convex problem, and in some cases there can be multiple local minima which are located in separate basins of attractions. So this is why this problem is really hard, and some authors have considered some simplified framework. There have been many attempts to solve this problem in the literature. I'm not going to explain all of them because it will require a tutorial on this only. So this is just a list of methods, even some recent one, and which all employ different techniques. Just to make some example, there are approaches based on Riemannian optimization or Lagrangian duality. And an important popular approach is also the one based on Lie group optimization, which is in some sense an intrinsic solution, because by exploiting this Lie group structure, the problem is solved in the tangent space, and this allows to remain in the group without needing a final projection. A final comment on rotation. In general, the problem of estimating absolute rotations from relative one is an example of a more abstract problem, which is called by some authors synchronization and averaging by others. And the task of this problem is to recover elements of a group starting from pairwise ratios. So in our case, the group is the group of rotations, but also other cases have been considered in the literature, such as the case of permutations for matching. And in this case, the unknowns are associated to the nodes, whereas the measures are associated to the edges. And with this graph representation, we only require a connected graph as assumption, whereas for a disconnected graph, we have multiple ambiguities. So the solution is not unique. And in addition, in this case, the minimal scenario corresponds to a spanning tree, where we have only a tree, and we can find a solution by setting the root, for example, to the identity and propagating our consistency constraint. So this concludes the part of rotations. We will later see the part of translation, and now we can either have questions or start directly with the break. And we will restart at 3:30. So if there are questions, please ask.
It's a naive question. It seems that all of the methods employ the relative rotation. There's no method that where you could just throw everything in and it does it all. In other words, is it necessary that the problem be broken down into many pairwise relative rotations?
I mean, it is not necessary, and the fact that I presented a taxonomy of approaches is to show that there are many ways to approach the problem. So this is just one possible solution, but there are also others, like the sequential approach, where you consider both rotation and translation in a way, and also points. And I will also briefly explain later that you can also consider rotation and translation in as a single matrix without splitting the problem.
But even in the sequential, it's the pairs that are in sequence. But there's no way to sort of, or maybe that.
I mean, the projective factorization is a way where you put all the points and you get everything. So this is an example of what you are asking.
Yeah.
Or
I thought there were a lot of RIJs in there also, which are relative.
yeah, but that RIJ have a different meaning, were not pairs of cameras, but they were one, for example, here, I is referred to the camera and J is referred to the point.
Oh, okay.
So this is represent the image and the point, but not up to cameras.
Oh, thank you.
Okay. If there are other questions, I'm here, otherwise we can have a break. Aspetta che devo rispondere. we can restart. Cosa? Sì, sì, fatto. Ok. So, before the break, we saw how to compute rotations in global structure from motion. And now we go back to the second step, which is computing translation. So, we saw before that we can represent relative and absolute poses using matrices of SE3, which represent both rotations and translation in 4x4 matrices. And we also saw that we can split the consistency constraint into rotation and translation. And now we focus on the translation part of the consistency constraint, saying that the relative displacement between two cameras is equal to the difference between the camera centers. And if rotations are known, and this is the case because they have been computed previously, this is a linear system. But the system is linear if relative displacement was completely known, but we have to deal with a problem that comes from the fact that we don't know the magnitude of relative translations, but we can measure only the direction. And this follows from the essential matrix decomposition, where, as explained this morning, from the essential matrix, we can recover only the direction of the relative translation, but not the magnitude. And this explains why before I told you that relative pose is not really known. And we denote here the direction as Uij. And the directions are our input. So we can express the problem of recovering camera positions as the problem of recovering the location of some nodes starting from pairwise directions. And as before, we can represent this as a graph where nodes correspond to our unknowns and edges correspond to the input, which are the known directions, which are measured from the essential matrices. And we can consider as a possible starting point the definition of a direction. So we can write the direction of between cameras I and J as the difference between the camera centers, which is normalized by their norm. And this is also called the direction constraint, and it is written for a single edge only. First, we write this in another equivalent form, similarly to what was done for other geometric problems this morning. Since we don't know the norm, we can write this constraint by observing that we require two vectors to be parallel. So we require the direction and the difference between the camera centers to be parallel. And this, as shown this morning, can be written as the cross product between the two vectors be equal to 0. And moreover, the cross product can be written in an equivalent form using a proper skew symmetric matrix, so that we get a more standard equation. This is a linear equation where the direction is known and the camera centers are unknown. And this is for a single edge, but we can stack these equations one under the other when we have multiple edges and write this as a single linear system where we can, in a standard form, like S times X equals 0, where X contains all the unknown camera centers one under the other. So it's an unknown variable of with the 3n entries, if n is the number of cameras. And the size of the coefficient matrix depends on the number of edges in the graph, which is m in this notation. As shown this morning, we can solve a homogeneous linear system in the least square sense using the singular value decomposition. However, it was noted by some authors that this least square solution has a problem, namely it suffers from the so-called clustering effect. In other words, it is possible that the camera centers can collapse to a few wrong locations. And in order to avoid this problem, we can include additional constraints in our optimization problem that essentially force the camera centers to be sufficiently distant. So we can enforce a constraint on the distances between the camera center, which are required to be sufficiently large. So, for example, we can set up a minimization problem where we minimize the difference between the direction multiplied by some scale and the difference between the camera center, where we add some constraints, such as the sum of relative of all the camera centers to be equal to 0. And this is just a way to fix the global ambiguity that in this case is only a translation ambiguity, since we are focusing on translations only. And moreover, we include a constraint on the unknown scales. These scales are unknown. I forgot on the minimization problem. And we require these scales to be larger than a given value, such as greater than 1. And this is the constraint that avoids the clustering effect. There has been multiple attempts to solve this problem, and I'm not going to go into details of all of these methods. Here is just a list of papers on this topic and a list of core techniques that are used. Just to make an example, some authors use, for example, convex programming or the alternating direction method of multipliers. We now go to the problem of which theoretical conditions are required by this specific approach. But in this case, the situation is quite easy because this is a problem which is studied in the literature under another name. In particular, in general, the task of estimating some nodes in the space from pairwise direction is also called bearing-based localization. And this is a well-studied task, mainly in the fields of discrete geometry or robotics. And here we ask for which graph we have a well-posed problem, where once again, nodes are unknowns, edges are measures. In this case, nodes are the positions of the cameras and edges are the directions. So it was shown that we have a well-posed problem. So we can recover uniquely the camera centers if and only if the graph has a geometric property which is called being parallel rigid. And the meaning of parallel rigid is the following. Here on the left, we have an example of a rigid graph. And in this case, all the possible configuration that keep edges parallel differ by translation and scale. Whereas if this is not the case, the graph is called flexible. And on the right, we have an example. And we can see, for example, that if we move this node along the direction and also here, we keep the edges parallel. So we have a parallel configuration, but it's not a translation or scaling of the original one. But there are also other types of transformations. And this is exactly the meaning of being flexible or on the other side rigid. So this is the assumption that we require to have a well-posed problem for camera location recovery. And in particular, it was proved that this notion of parallel rigidity can be reduced to checking properties of the graph only if we are in a case of a generic configuration. So, for example, cameras that do not lie on a line or on a plane. Here are just some examples of sufficient or necessary conditions for parallel rigidity that help to have some intuition on the problem. For example, if we have only one cycle, then it was proved that it is rigid only if it has length 3 or 4, whereas longer cycles are flexible. And in terms of necessary conditions, it was proved that if there are articulation points or bridges, then the graph is not rigid. And this means that we disconnect the graph if we remove one node or an edge. And if we play with these conditions together with the fact that union of rigid graph with common edges is also rigid, then we can construct a lot of examples of rigid or non-rigid problems, such as the one in this figure. And it's important to have some interpretation of the problem because we will see that it is not the case for a related problem of solvability that we will see later. And these conditions shown in the previous slide are just to give some intuition, but in terms of algorithm and testing parallel rigidity, this is a simple problem because we can check if a problem is rigid or not just by checking the rank of the equation associated to the localization problem, where the rank is not the maximum value because we have both translation and scale ambiguity. So the rigidity condition means that the rank is the maximum values minus 4. And just to summarize, if a graph is rigid, then recovering camera positions from directions is well posed, whereas if it is not the case, then we have an ill-posed problem with multiple solutions. And in this case, we need to reduce the problem to the largest rigid component. And there are algorithms for doing so based on clustering the rows of null space matrix. Here, I reported some statistics related to some graphs of popular datasets which are used in structure from motion. And you can see that being rigid is not very common, as in this data set, only one case is rigid, but all of the others have both articulation points and bridges. And in particular, to visualize one example, here I reported a simplified representation of the R-squared data set, where only the edges out of the largest component are drawn, just to see which are the reasons that cause the graph to be non-rigid. But however, we do not need to worry too much because we just have to reduce our problem to the largest rigid component and hence perform the global structure from motion on a reduced set of cameras. So just to summarize the global structure from motion, our input is a set of correspondences and calibration matrices, and then the focus is on motion estimation, which in turn is split into solving for rotations, then extracting the largest rigid component if needed, and then solving for camera centers by viewing the problem as a localization problem. Then, as anticipated before, if motion is known, then we can recover structure by standard techniques such as triangulation and refining our solution with bundle adjustment. So this is a possible attempt for recovering the motion in structure from motion, but we can also adopt a different approach where rotations and translations are not considered separately, but they are jointly recovered in the special Euclidean group. However, we cannot directly work on the special Euclidean group because we have the problem of unknown scales. And so we need to either iteratively or in closed form, recover these scales. And for example, we can recover the scales by an iterative approach that set all the scales to a fixed value like 1 and then update the scale based on some current solution. Or in alternative, we can explicitly recover these scales by exploiting the property of cycle consistency. And this means that we can use the constraint that the sum of displacement along cycles is 0, and this can be viewed as an equation in the unknown scales. And then we can use similar approaches that were in the special Euclidean group instead of the group of rotations if the scales are known. Some comments on global structure from motion. These methods are usually both faster and require less memory than sequential or hierarchical methods because they do not work with the points, but only in the space of transformations. Moreover, they are global because they consider all the graphs simultaneously, and this promotes error compensation. So they can be viewed as an effective way to compute an approximate solution for camera motion, which is then refined by bundle adjustment. As a drawback, we have suboptimal accuracy because we don't use points, so we are losing some information. And also, we require redundant measures. So in practice, this method does not work well if we have a minimal number of measures. But redundancy is important for achieving an effective error compensation. Now I will explain another approach, which is based on a multi-view fundamental matrix, which is still within the category of motion first approaches. And it can be viewed as the uncalibrated version of global structure from motion. So the pipeline is the same as global structure from motion, but we do not require the calibration matrices as input. But for the rest, it's the same. The focus is on motion only, and then structure estimation is standard and final refinement is always applied. Accordingly, the problem formulation is quite similar to global structure from motion, in the sense that we split the motion stage into steps. First, we compute for each image pair the fundamental matrix, using, for example, the 8-point algorithm reviewed this morning. Then, starting from these fundamental matrices, we recover the projection matrices of all the cameras. So, as shown in the figure, in the first step, we recover fundamental matrices for many pairs of cameras, and then we will use this as input to an algorithm that return camera motion. Some observations made for structure from motion apply also here. In particular, in the first step, we have some local or relative information because we consider only an image pair. Whereas in the second step, we work with global or absolute information because we consider all the cameras simultaneously. However, here, in contrast to the calibrated case, relative and absolute variables have a different form because before, both relative and absolute quantities were rotations, whereas here we have fundamental matrices and camera matrices, which are different things. Moreover, similarly to before, we do not use correspondences in the second step, but we use matching points only to recover the fundamental matrices. This means that after the first step, points are not used, but we will use only the fundamental matrices. So this approach is based on a recent paper, which defines a big matrix which stores all the fundamental matrices, and this is called multi-view fundamental matrix. So the construction is quite similar to our big matrix with all the rotations. For example, in the block associated to the first row and second column, we put the fundamental matrix relating cameras 1 and 2. And similarly for all the blocks. And here we have a matrix with size 3n times 3n, with n is the number of images or cameras, and this is symmetric due to properties of the fundamental matrices. We make two simplifications. We consider for the moment a complete graph, meaning that here we know all the possible fundamental matrices between all the pairs of cameras. And moreover, the theorem that I will explain in a while holds only if each fundamental matrix has some proper scale, but it does not work if we put some random scales. And recall that this is a problem because fundamental matrix is a projective quantity that is defined up to scale. But for the moment, we assume that the graph is complete, so we have all the fundamental matrices, and also in these constructions, there are some proper scales. So it was shown by the authors of this paper that we have a consistent multi-view fundamental matrix, meaning that it defines a set of camera matrices if and only if two conditions are satisfied. The first is that the multi-view fundamental matrix has rank 3, and it has exactly 3 positive and 3 negative eigenvalues. And the second is that the rank of each block row, so for example this, is 3. And this holds for all the blocks. Moreover, the authors show that if these conditions are satisfied, then it is possible to recover the camera matrices from the eigenvalue decomposition of the multi-view fundamental matrix. So this theorem gives us some conditions under which it is possible to recover the cameras from the multi-view fundamental matrix, and also some instructions to do it. However, it is not so easy to use this theorem because of the two assumptions that we made before. So the problem of these unknown scales and also the problem of missing data. So how can we deal with these unknown scales, missing data, and also the problem of noise? So the authors of the previous paper develop a method based on this result. So they observed that if we focus on the case of 3 views, so we have a 3-view fundamental matrix, then this is invariant to arbitrary scaling of the constituent fundamental matrices. So this means that if we put some arbitrary random scales, then this does not affect the result in the case of 3 views only. And this was the main motivation to build a method based on triplets. So as a first step, the graph is divided into triplets. So a triplet cover for the graph is constructed, as shown, for example, in the middle figure. And then for each triplet, camera matrices are recovered. In order to do this, for a triplet of images, the results of the previous slide is used. So the idea is to optimize over fundamental matrices by enforcing the properties of the theorem. So we have some properties in terms of rank. So given a 3-view fundamental matrix, we can recover a refined fundamental matrix that satisfies these properties using rank constraint optimization. For example, the alternating direction method of multipliers can be used. And this gives us some refined fundamental matrices for a triplet, and then we can recover the camera matrices using the previous result. So from the eigenvalue decomposition of the multi-view fundamental matrix. This is applied to each triplet of cameras. And then at the end, all these independent reconstructions are brought to a common reference frame. Also in this case, we consider the question of which graphs have a well-posed program. We call the graph a viewing graph, and we say that the problem is well-posed when the graph is called solvable, meaning that all the fundamental matrices determined the camera matrices uniquely, so up to a single projective transformation. And this means that there is only one single ambiguity to our problem. And recall that this ambiguity is inherent to the problem and cannot be avoided. So the point is to make it a single projective transformation. If this is not the case, then we say that the graph is non-solvable. Similarly to the case of parallel rigidity, under the assumptions of generic configurations of cameras, then it can be proved that this concept depends on the graph only. So this problem is not much studied in the literature. In terms of necessary conditions, it was proved that a solvable graph is biconnected, and this is the same result as the calibrated case. And moreover, there is a condition on the number of edges. So a solvable graph needs to have at least this value of edges, this amount of edges. So if there are too few edges, then it is not solvable. And these are conditions which are really easy to check. Moreover, there exist also some sufficient conditions in the literature. In particular, it was shown that if a graph is triangulated, then it is solvable. So a graph made of triangles is solvable. And in particular, this explains why the method explained before works, because it's based on triplets. Moreover, there exist also some constructive approaches that, given a graph, they modify it into some cases which are known to be solvable. And in terms of characterizations, the situation is much more complicated, because the unique characterization which is available in the literature is a polynomial system which has a large number of unknowns, and this requires Grobner basis computation to find a solution. It is possible to simplify the problem, in particular to eliminate some variables by exploiting cycle consistency. And this allows to increase the size of the graphs that can be checked up to graphs with 90 nodes, but at the moment, larger cases cannot be checked. And moreover, in this figure, there are some examples of solvable graphs, but however, or at least in my opinion, in contrast to the case of parallel rigidity, here it is hard to have some intuition about which cases are solvable and which cases are not solvable in terms of the structure of the graph. Some observations about this approach. As already mentioned, it can be seen as the uncalibrated version of global structure from motion, and so we can make similar conclusions about the advantages and disadvantages of this approach. But however, as mentioned in the previous slide, the uncalibrated scenario is much more difficult. For example, we cannot check the solvability for large problems. There are also some extension of this approach which focus on degenerate cases, such as the scenario of collinear cameras. So now we move to the last category of the structure from motion taxonomy, which is what I call the structure first. So to recap, I explained that global structure from motion focuses on motion estimation because with known motion, then structure estimation is straightforward. However, it is also possible to directly estimate the structure without explicitly recovering camera motion. And for this reason, I call this approach structure without motion. Okay, in this case, we are not seeing all the details, but I will just give you some intuition. So the idea here is to focus not on the coordinates of the 3D points, but on the distances between 3D points. And this is motivated by the fact that with known distances, then recovering the coordinates of 3D points can be done by using standard tools, such as the multidimensional scaling. So the focus is on recovering distances between 3D points. And also here we use a graph representation, but it's different than the graph used in the previous problems. So here nodes are not only camera centers, but can be both camera centers, like these three, and 3D points, like here. And moreover, concerning edges, we proceed as follows. We say that two 3D points are connected by an edge if their image points are seen by two or more cameras simultaneously, like in this figure. And in this case, we also put edges between camera centers and the 3D points. So this is our construction of the graph. Nodes are either camera centers or 3D points, and edges encode 3D points viewed by multiple cameras simultaneously. So this is the basic equations that is used by this approach, and this basic equation considers a triangle only, and it uses the law of cosines. So first, let us introduce some notation. We denote by L the distance between the 3D points. Moreover, we denote by xi the distance between 3D point A and the camera center. And similarly, we denote by xj the distance between the second 3D point and the camera center. And moreover, we denote by theta the angle between the optical rays going from the camera center. So the law of cosines tells us that the square distance xi plus the square distance xj minus twice the product between xi, xj, and the cosinus of the angle is equal to the square distance between the 3D points. And in this equation, the unique variable which is known is the angle between the camera center and the two 3D points, which can be computed from the calibration matrix as shown this morning. So in this equation, all the variables are unknown except of the angle. And this equation is also the same as the basic equation of the perspective and point, but here we have more unknowns. So, with some computation, it is possible to write this equation when considered for all the edges simultaneously, as a semi-definite program. And so we can solve structure without motion using semi-definite programming. So, also in this case, there are some theoretical conditions that ensure that the problem is well posed. So since we are working with distances, we are in a scenario similar to the fixed length bars connected by joints, where we know the distances, we don't know the coordinates, and we ask if the distances uniquely determine the coordinates up to rotation, translation, and reflection. And this is another type of rigidity, which is called the distance-based rigidity, and is a different concept than parallel rigidity. And in the figure, you can see some examples. And moreover, here we are considering a different graph than global structure from motion, because we are using both cameras and points. I'm not going to go into the details of distance rigidity, just to have some intuition. It's the same as playing with geomag, so seeing which configurations are possible with fixed distances. And this concept can be checked using linear algebra tools, so by checking the rank of some proper matrix. So to summarize this approach, we are in a calibrated setting. As always, our input are a set of correspondences, and this is the dual of global structure from motion. So we focus on recovering the structure only. So as a pre-processing, we check if our problem is well posed by checking distance-based rigidity. Then we compute the distances between 3D points by solving a semi-definite program. And finally, we recover the coordinates of the points starting from the distances. And this gives us the camera centers. No, not the camera centers, the 3D points. Then I call this approach structure without motion, but in principle, if one is interested in motion, it can be computed after structure. And in this case, we know 3D points, so the structure. We also know 2D points that are the input correspondences. So this is a problem with known 2D, 3D correspondences, which can be solved with resection or PNP, by solving a PNP problem. As always, at the end, we refine our solution using boundary adjustment. So some summary on this approach. This is a direct approach because it has eliminated the need for estimating motion parameters if one is interested only in the 3D reconstruction. It's also a global approach because it considers all the graphs simultaneously, but is computationally expensive because it's based on semi-definite programming. There are also some alternative approaches in the literature, but they are all non-linear. One is based on eliminating some variable, so algebraic variable elimination. And also it is possible to have some simplified informulation in the special case where we have planes in the scene. So we work with homographies. Okay, so this concludes the taxonomy of structure from motion. Now I have some concluding slides, but if you have some questions at this point, you can ask now, and then we move to the conclusion. Can you go to the microphone?
Hi, thanks for the tutorials. I have a general question. What can you do if, in addition to RGB images, you have depth as you capture your data as a LiDAR, for instance? How can this information be incorporated into the
I will say that if you have LiDAR, then the program is much simple because you already start with 3D. Whereas in structure from motion, you start from 2D and you go to 3D with geometry only. So starting with 3D simplifies the problem.
You mentioned at the start, we have an assumption of aesthetic scene.
Yes.
What happens when it's a dynamic scene? Like
No.
how much is there any robustness, like the small changes or?
No, all the things I explained are with a static scene. If you have a dynamic scene, then the problem is much more complicated. It's called the multi-body structure from motion, and it's like a combination of two different problems. One is structure from motion, so reconstructing the scene, and the other is motion segmentation, so identifying which parts of the images are moving, and so you need to solve these two problems in a combination.
I have a question on multiple fundamental matrices. I was curious, like how it is advantageous to do multiple view fundamental matrices, or should I do motion average?
The difference is in the scenario because motion averaging is for calibrated cameras, whereas multi-view fundamental matrix is uncalibrated.
Okay. One question is like, because from practice, motion averaging is very fast. How about the fundamental?
I haven't experienced personally with the method, but I will say that it is fast because it splits the problem into triplets. But it's still not a general method because it works with the triplets only, so it does not work with general graphs.
Also, like, is it essential criteria to have a bundle adjustment after motion averaging? Motion averaging is fine after.
In general, the quality of the reconstruction by averaging is good, but bundle adjustment improves further the results. So it is always recommended. Okay.
Yeah, this one.
Okay.
Is it essential or non-essential for like
Can you repeat?
So like what's the full matrices or not? Like if I say that if I estimate that is it gonna be
This theorem works in the noiseless case. So F21 and F12 are symmetric.
I've seen that, but if I'm using it, my calculator to estimate layer.
But you can estimate only once and then have put the corresponding results in the other edge.
A couple of questions. And, we were talking about the rigid versus the flexible. Could you describe, if you just had a chain of poses that are put together, would that be considered rigid, or would that be considered just a graph? It's a chain of poses, is that considered rigid or flexible?
No, this is flexible, but this, as I mentioned, each condition was associated to a specific approach for structure from motion. So this is rigid when solved in a, this is not okay if you follow a global structure from motion version. If you use another approach with points like sequential structure from motion, then it's okay.
Yeah, I understand. Okay. And then just this is a separate topic, but when doing bundle adjustment and outputting the, I didn't see any description of like error covariance, uncertainty quantification of the poses or the points. Is that something I've seen that you can sometimes get formulations for errors, covariance of the points out with? Is
Yes.
that something that you've seen or shown real well?
I didn't have experience with this topic, but for sure it exists.
Okay.
Okay, so okay, the final part of our tutorial are a few slides which speak about some research areas which are related to the topic that we presented today. So in the morning, we saw multiple tools from multi-view geometry, like some basics about camera model, fundamental metrics, and so on. And in the afternoon, we saw how to perform an image-based 3D reconstruction pipeline. So you may ask if this is all the stuff or if these topics are still explored. And the answer is yes, because there are many examples of active research areas which are related to the topics of this tutorial. I prepared a list of examples, but of course, this is not exhaustive. There are many other interesting topics that are being researched nowadays. So this list includes combinations of geometry and deep learning, theoretical aspects of computer vision, the problem of averaging or synchronization, and finally, robust fitting and minimal problems. First, and many of these, some of these topics also include papers that won prestigious prizes at top conferences. So, concerning combination of structure from motion and deep learning, it was recently proposed an approach that performs a feature metric refinement in structure from motion that won the best student paper last year at ICCB. And the idea here is to focus on the correspondence part of structure from motion, which was assumed as input in this tutorial, and combine both sparse features and features extracted with a deep network in order to do this feature metric adjustment. And the idea is to improve with deep learning the input correspondences to structure from motion. And this refinement is also applied at the end when applying bundle adjustment in order to produce a refined reconstruction. Another example of approaches that combine structure from motion and deep learning is the usage of graph neural network for the rotation part of global structure from motion. And the idea is that since the problem has a natural representation in terms of a graph, the usage of graph neural network seems natural. And in this context, one of the most popular approaches is the Neurora paper, which splits the problem into two different networks. One focuses on refining the relative rotations, so a sort of denoising. And then another network focuses on refining the final rotations. And this also uses some intermediate traditional step for initializing the rotations. And there has been several improvements, and there is also a paper on this topic presented at this CVPR. Another example is the usage of an encoder architecture for projective factorization. And in particular, the authors of this recent ICCV paper focuses on the property of being permutation equivariant, meaning that if we change the order of points or cameras, the result should not change. And this important property is used within the network, which is trained according to a loss based on the reprojection error. More general, if we consider the problem of combining geometry and deep learning, there are still a lot of questions which are explored and where it is hard to find a general answer because it is problem dependent in many cases, like how to bridge the gap between geometry and deep learning, or which are the meaningful mixture between neural and optimization methods, or if it makes sense to use learning if we have some analytical expressions. And in this context, a powerful tool is the framework of deep declarative networks, which proposes a new way to see deep learning because they consider cases where we do not have an explicit formula for the forward function, but it is implicitly defined as the solution of an optimization problem. And this idea can be used to include optimization problems coming from geometry within a deep network. And the authors of this recent PAMI paper show that it is possible to perform back propagation by using the implicit function theorem. Another example of research problem that is still has some open issues is the topic of the theoretical aspects of structure from motion. From my presentation, you saw different formulations of structure from motion, like the calibrated or the uncalibrated scenarios, the case where we use points, or the case where we use only reference frames or transformations. And I show you that each formulation has different theoretical assumptions. But a unifying view of all these different assumptions is still missing. And in particular, some open issues are related to a specific theoretical aspects, which is the case of uncalibrated solvability. So the case of when a structure from motion problem is well posed, if we use the multi-view fundamental matrix. As explained, this is a hard task. So it involves a polynomial system of equations, and the current solutions are not scalable. So the paper I co-author mentioned below brings a significant improvement in the state of the art by managing graphs up to 90 nodes, whereas previous papers focuses on 9 or 10 nodes, but this is still far from the calibrated case where we can manage hundreds or thousands of images. And moreover, we do not have an interpretation of the problem in terms of graph topology. And this is different from the parallel rigidity case that refers to calibrated structure from motion. Another example of a problem which is still investigated is the topic of averaging or synchronization, where the general task is the following. We have a graph where The objective is to recover some unknown global variables, starting from pairwise measures, where unknowns are associated to nodes and measures are associated to edges, and all these variables are represented as elements of a group. In this tutorial, we saw the case of rotations, which is related to structure from motions, but there are also other examples, like the case of registration of 3D point clouds, where the group is the set of rigid motions, or the case of multiple matching, where we have permutations, or also the case of motion segmentation and image mosaicing. In particular, recent papers are, for example, following on new scenarios, like the case where we have a multi-graph instead of a graph. So we have multiple edges between two nodes, or on specific applications like part segmentation in point clouds, or on new approaches based on a probabilistic framework. Moreover, there are also many authors which are focusing on the problem of finding some optimality guarantees. And this is an important theoretical property of a method. Another topic which is still being explored is the topic of robust fitting. We saw this morning, for example, ransack and its variations, and this is still explored. There are many research directions related to robust fitting, so this is just one example. That is the usage of quantum algorithms for robust fitting. And this is motivated by the fact that quantum computers can solve hard combinatorial problems. At the moment, they cannot solve large-scale problems, only small cases, but it is expected that the quantum hardware will improve in future years. So we expect to see more practical advantages over the year. And there is also a paper at this CVPR on this topic. Concerning robust fitting, we saw this morning the case where we want to fit one single model, but there is also the case where we want to fit multiple models. And this is much harder than the case of single models, because this problem has a chicken and egg structure, meaning that we need both to estimate the models and also to segment or cluster the data. And here is still explored from several perspectives, like focusing on the case where we have heterogeneous structure, like fitting both planes and cylinders, or focusing on using deep learning for a specific step of robust fitting, like the sampling step, or focusing on exploring the advantages of trifocal constraints, or on specific algorithmic aspects, like being efficient and anytime. Finally, another related topic is the case of minimal problems. And these are the key building blocks of robust fitting methods, because typically when in the step of sampling, we use minimal solver to produce our candidate solutions. And there is a work on this topic that won the best student paper at ICCV 2019, which focuses on a classification of the minimal problems in the specific case where we have points and lines in images which are seen in all the views. There are also other works focusing either on a specific application like panoramic stitching, or focusing on providing a good solver, which is presented at this CVPR. So this ends our tour in multi-view geometry. We hope you enjoyed it, and thank you for your attention. for any questions. Either go to the microphone or we are here for discussing.
So there wasn't much discussion of it explicitly of occlusions. So when there's occlusions, so that, you know, the same point cannot be seen by multiple cameras, how does that factor in?
This is the case where we have some missing points and multiple methods are managing this. The important thing is that this occlusion does not involve all the images, but only some of them. So we can compensate this missing information with information that comes from other images.
So many questions. We can solve the structure without, we can solve motion without the structure. Why we call it structure?
I forgot to say this, but when I prepared the slide, I wanted to mention, you are right, it's typically called structure from motion, but this name is correct only for global structure from motion, where structure comes later. But
so many things they want to resolve.
you are right. Okay. For we have finished a bit early. You are free to go out. If someone wants to discuss, we will be here. Bye.